The file is thick, bound in imaginary leather, and sits on a desk that exists nowhere and everywhere at once. Tonight we open it not to witness drama, but to review paperwork. This is the incident report of a supernova, and like all good reports, it begins not with the ending, but with a long period of absolutely nothing going wrong. The star in question, let's call it by its catalogue number, though it had no name when it lived, operated within normal parameters for millions of years. Its file contains entry after entry of routine measurements, core temperature stable, luminosity within expected range, radius showing minor fluctuations consistent with convective activity. For a massive star, this period of nominal performance is almost embarrassingly uneventful. The star began its life as many massive stars do, from a cloud of gas and dust that happened to have enough material in one place to start collapsing under its own gravity. As the cloud fell inward, it heated up. Eventually, the center became hot and dense enough that hydrogen nuclei began to fuse into helium, and at that moment the star turned on. This ignition point is recorded in the file as the beginning of the main sequence phase, the long stretch of time when a star does the one thing it was built to do: convert hydrogen into helium in its core, release energy, and use that energy to push back against the gravity trying to crush it. Hydrostatic equilibrium is the technical term, a fancy way of saying that the star found a balance. Gravity pulled inward with steady force, and the pressure from hot gas and radiation pushed outward with equal determination. As long as this balance held, nothing interesting happened. The star simply existed, burning through its hydrogen fuel at a rate determined by its mass, shining steadily into space, a well-behaved employee clocking in and out for millions of years without filing a single complaint. The file notes that this star had a mass somewhere around 20 times that of our Sun, which sounds impressive but comes with a cost. Massive stars burn brighter and faster than their smaller cousins. Where a star like our Sun can maintain hydrogen fusion in its core for roughly 10 billion years, this star exhausted its core hydrogen supply in just a few million years. The log shows a gradual transition, as hydrogen in the central region depleted and helium accumulated. Eventually the core became so helium-rich that hydrogen fusion could no longer continue there. This did not mean the star stopped working. Hydrogen burning simply moved to a shell surrounding the now helium core, and the star entered a new operational mode. The file documents this as a fuel transition, routine for stars of this mass class. But helium itself is a fuel, and the core did not sit idle. As the hydrogen-burning shell dumped more helium ash onto the core contracted and heated up. When temperatures reached roughly 100 million degrees, helium nuclei began fusing into carbon and oxygen through a process called the triple alpha process. 3 helium nuclei combine to make carbon. Sometimes a 4th helium adds on to make oxygen. This new fusion process released energy, re-establishing pressure support in the core. The file logs this as the helium-burning phase, noting changes in the star's surface properties, an increase in radius, a shift in colour, but nothing that would trigger an alert. The star was still following its design specifications, adjusting to new fuel as the old fuel ran out. In a less massive star, this might be the end of the story. A star like the Sun will never achieve the core temperatures needed to fuse carbon. It will shed its outer layers as a planetary nebula and settle into retirement as a white dwarf. But our star, massive and hot, continued. As helium burning proceeded, the core filled with carbon and oxygen. When helium became scarce in the center, helium burning moved to a shell, and the carbon-oxygen core contracted and heated further. At around 600 million degrees, carbon nuclei began to fuse, producing neon and magnesium. The file now shows an accelerating pattern. Each new stage of fusion runs hotter, denser, and faster than the last. Carbon burning lasts only a few thousand years. After carbon comes neon burning, lasting roughly a year, then oxygen burning, lasting only months. The star has become an onion of shells, each layer fusing different elements, each deeper layer hotter and more compressed than the one above it. The incident report carefully lists these transitions without judgment. Fuel upgrade, carbon to neon and magnesium. Fuel upgrade, oxygen to silicon and sulfur. Core composition transition proceeding within expected tolerances. If you were reading this file during any of these phases, you would find nothing alarming. Just a star aging through its natural life cycle, checking off milestones on a predetermined path. But then, buried in the technical notes, a line appears that will become important later. Non-fusible core product accumulating. Silicon burning is the last stage that produces net energy. When silicon nuclei fuse at temperatures around 3 billion degrees, they build up heavier elements through a cascade of reactions, ultimately producing iron, cobalt, and nickel, elements clustered around iron in the periodic table. Here the file flags a condition that changes everything. Iron group elements are special in the worst possible way. For all lighter elements, fusing nuclei together releases energy because the resulting nucleus is more tightly bound than the ingredients that went into it. This released energy is what powers stars, what allows them to generate the pressure needed to resist gravity. But iron sits at the peak of the binding energy curve. Fusing iron into anything heavier does not release energy, it consumes energy. Iron is a dead end. It is ash that cannot burn. The report documents this transition in dry language. Core, composition shifting toward iron group elements. Fusion energy output declining in core region. Core mass accumulating at center with no pressure contribution from fusion. The star is still shining brightly on the outside. Shells of silicon, oxygen, neon, carbon, and helium continue burning in layers around the iron core, dumping their products inward. From a distance, the star looks fine, perhaps a bit bloated, perhaps showing some instability in its outer layers, but nothing that screams imminent disaster. Inside, however, the iron core grows quietly, gram by gram, adding mass in a place where mass is a problem. The core is now supported not by fusion pressure, but by electron degeneracy pressure, a quantum mechanical effect that arises when electrons are packed so closely together that they resist further compression. This is the same pressure that holds up white dwarfs, those dense remnants of lower mass stars. It is a strong force, capable of supporting significant mass, but it has limits. The file shows periodic entries as the core mass increases, core mass at 0.8 solar masses, core support margin adequate, core mass at 1.2 solar masses, support margin decreasing, core mass at 1.3 solar masses, approaching design limits. The language is careful, technical, bureaucratic. There is no panic in these entries, only a trend. The numbers are moving in a direction that cannot be sustained indefinitely. The critical point, the moment when the safety systems can no longer cope, occurs when the core's mass approaches the Chandrasekhar limit, roughly 1.4 solar masses. At this threshold, electron degeneracy pressure becomes insufficient. The core's density is so high, and the gravity pressing inward is so intense, that even the quantum resistance of tightly packed electrons cannot hold the line. Additionally, at these extreme densities and temperatures, energetic photons begin to break apart iron nuclei into lighter particles, removing energy from the core rather than adding it. Electrons begin to be captured by protons, forming neutrons and neutrinos in a process that removes the very particles providing the degeneracy pressure. The support structure is not just weakening, it is being dismantled from within. The incident report marks this moment with a stark entry: loss of structural integrity in core region. Timestamp recorded. Support systems failed. This is the violation of operating limits, the sudden transition the file has been quietly predicting for pages. In a fraction of a second, the core that had been hovering at the edge of stability tips over into freefall. Core collapse is not a slow, graceful descent. It is a catastrophic failure that occurs faster than sound can travel through the stellar material. The inner core, roughly the size of Earth, collapses inward at speeds approaching a quarter of the speed of light. In less than a second, it compresses from a sphere of iron nuclei and electrons into a sphere of neutrons packed to nuclear density. The file attempts to document this. Core radius decreasing, density increasing exponentially, core material reconfiguration in progress. But the numbers are so extreme that they strain the format of the report. Densities reach hundreds of millions of tons per cubic centimeter. Temperatures surge into the hundreds of billions of degrees. The electrons and protons in the core combine into neutrons, releasing a torrent of neutrinos that pour out through the overlying layers of the star. In the span of a heartbeat, the star's iron core transforms into something that resembles a single giant atomic nucleus, held together not by electron clouds but by the nuclear force itself. At nuclear density, the collapse halts. The core has reached a state where neutron degeneracy pressure the quantum resistance of neutrons packed to the limit can finally provide support. But the material still falling inward does not receive this message in time. The infalling matter slams into the rigid neutron core and bounces. This rebound launches a shockwave outward through the star. The incident report files this under shock formation and revival, though the word revival is a polite understatement. The initial shockwave, carrying the mechanical energy of the core's rebound, begins to race outward through the layers of silicon, oxygen, neon and carbon that still surround the core. For a moment it looks like this shock will simply blast through the star and eject the outer layers in one clean sweep, but the shock stalls. As it moves outward, it loses energy. It must push through dense material, and it must break apart the heavy nuclei in its path, dissociating them into protons and neutrons, a process that consumes energy rather than releasing it. Within milliseconds, the shock front weakens and grinds to a halt somewhere in the outer core, a few hundred kilometers from the center. The report notes this stall as a secondary complication, a moment when the expected sequence does not proceed as initially hoped. If the shock remains stalled, the outer layers of the star will simply fall down onto the neutron core, and the event will produce no visible supernova at all. Just a star that suddenly disappears, its mass swallowed into a black hole. What revives the shock is subtle and still not entirely understood in all its details, but the primary mechanism involves neutrinos. The collapsing core produces an extraordinary number of neutrinos, more than 10 to the power of 58 of them, carrying away almost all the gravitational binding energy released by the collapse. Neutrinos interact so weakly with matter that they pass through most material as though it were not there. But in the extreme densities just outside the neutron core, a tiny fraction of these neutrinos are absorbed by the infalling material, heating it and adding pressure behind the stalled shock. Over the course of a few hundred milliseconds, this neutrino heating revives the shock, giving it the energy it needs to continue its outward journey. The file documents this as shock revival via neutrino energy deposition, a technical phrase for a process that determines whether the star explodes or quietly implodes. With the shock reinvigorated, it accelerates outward through the star. It plows through the silicon shell, the oxygen shell, the neon shell, and the carbon shell, heating and accelerating these layers as it goes. When it reaches the hydrogen and helium envelope, it accelerates the outer layers to speeds of thousands of kilometers per second, launching them into space. This ejection of the envelope is what observers see as a supernova. The shock wave heats the expanding material to tens of thousands of degrees, causing it to shine brilliantly in visible light. The star, which had been a relatively stable point of light for millions of years, suddenly brightens by a factor of billions, becoming briefly visible across the galaxy, or even from neighbouring galaxies. The incident report records this as outer stellar layers removed and dispersed into surrounding medium, with parameters logged: kinetic energy of ejected material approximately 10 to the 51 ergs, total ejected mass approximately 10 to 15 solar masses. Composition includes hydrogen, helium, oxygen, carbon, neon, magnesium, silicon, sulfur, and trace heavier elements. At the center of this expanding debris cloud, a compact remnant remains. The final entry in the core disposition section depends on the mass that stays behind after the explosion. If the neutron core's mass is below approximately 2 to 3 solar masses, neutron degeneracy pressure is sufficient to hold it up indefinitely. The result is a neutron star, an object roughly 20 kilometers in diameter, but containing more mass than the Sun, spinning rapidly and often beaming radiation from its magnetic poles. The file notes the formation of a neutron star with initial spin period, magnetic field strength, and surface temperature recorded for future reference. If the remnant core's mass exceeds the limit that neutron pressure can support, the collapse continues past the neutron star stage, and the core becomes a black hole. In that case, the report lists core disposition as black hole formation likely, mass approximately 3 to 10 solar masses, event horizon established, no further direct observation possible. Not all supernovas follow this core collapse pathway. The incident file includes a separate section for a different failure mode, one that occurs in a completely different type of star. Type Ia supernovas involve white dwarfs, the dense remnants of lower mass stars that have already completed their main life cycle. A white dwarf is a compact object, roughly the size of Earth, composed mostly of carbon and oxygen and supported by electron degeneracy pressure. On its own, a white dwarf is stable and will remain so indefinitely. But if the dwarf is part of a binary system, circumstances can conspire toward a different ending. If the white dwarf has a companion star close enough to transfer material, the white dwarf can slowly gain mass by accreting gas from its partner. This process can continue for thousands or millions of years, with the white dwarf growing heavier as matter spirals down onto its surface. Alternatively, two white dwarfs in a tight orbit can gradually lose energy to gravitational radiation and spiral together, eventually merging into a single, more massive white dwarf. In either scenario, the white dwarf approaches the Chandrasekhar limit. The incident report for such a system shows a gradual build-up, white dwarf mass increasing, degenerate carbon-oxygen core near critical mass, core temperature rising due to compression but fusion not yet initiated. When the white dwarf's mass reaches the critical threshold, the carbon in its interior becomes hot enough and dense enough to ignite, but it does so under degenerate conditions. In a normal star, if fusion starts to run away and release extra energy, the star heats up, expands and cools down, providing a natural thermostat. In a degenerate white dwarf, the pressure is provided by electron degeneracy, which does not depend on temperature. This means there is no thermostat. Once carbon fusion ignites, the temperature rises, which increases the fusion rate, which raises the temperature further, creating a runaway feedback loop. In less than a second, a flame front races through the entire white dwarf, burning carbon and oxygen into iron group elements and releasing enough energy to completely unbind the star. The white dwarf explodes, leaving nothing behind. No neutron star, no black hole, only an expanding shell of debris moving at speeds of 10,000 kilometers per second or more. The report for a Type Ia supernova lists the pre-event state as degenerate carbon-oxygen core near critical mass, followed by runaway thermonuclear disruption, and concludes with complete stellar disruption, no compact remnant, ejecta composition dominated by iron, cobalt, nickel, and intermediate mass elements. These events are slightly less energetic than the most powerful core collapse supernovas, but they share a common feature. They are extremely bright, and because the white dwarfs that explode all have similar masses, close to the Chandrasekhar limit, the resulting supernovas have similar peak luminosities. This uniformity makes them useful. Astronomers use Type Ia supernovas as standard candles for measuring distances across the universe. Because their peak brightness is consistent, observing how bright they appear from Earth allows a calculation of how far away they are. The incident report classifies them under a consistent category with predictable luminosity curves, making them valuable reference entries. In the 1990s, observations of distant Type Ia supernovas revealed that the expansion of the universe is accelerating, a discovery that led to the inference of dark energy. From a paperwork perspective, these supernovas are logged with coordinates, light curves, spectra, and distance estimates, and their collective data fills in the cosmic distance ladder, helping to map the universe's expansion history. Supernovas do more than mark the end of stars, they also create. The incident report includes a byproducts section, a detailed accounting of the heavy elements produced and ejected during the explosion. In core collapse supernovas, the extreme conditions during the collapse and explosion allow rapid neutron capture processes to occur. Nuclei are bombarded with neutrons, building up elements heavier than iron, elements like strontium, barium, and even gold and platinum. These elements cannot be made by normal fusion in stars. They require the neutron-rich environment of a supernova or neutron star merger. The explosion spreads these newly forged elements into the interstellar medium, enriching the gas that will eventually form the next generation of stars and planets. Type Ia supernovas contribute primarily iron group elements, iron, nickel, cobalt, along with intermediate mass elements like silicon, sulfur, and calcium. The explosion synthesizes roughly half a solar mass to a full solar mass of radioactive nickel-56, which decays into cobalt-56 and then into stable iron-56 over the following months. This radioactive decay powers the supernova's visible light curve, causing it to shine brightly for weeks and then gradually fade. The report lists updated abundance tables, noting how much of each element was added to the surrounding space. So many solar masses of oxygen, so much silicon, so much iron. Over billions of years and countless supernovas, these contributions build up the heavy element content of galaxies, allowing planets like Earth, with their iron cores and silicon crusts, to form. After the initial explosion fades, the debris does not simply disappear. It expands outward at thousands of kilometers per second, slamming into the surrounding interstellar gas and sweeping it up into a growing shell. This interaction creates a supernova remnant, a structure that glows at multiple wavelengths as the shockwave heats the gas and accelerates particles to relativistic speeds. Observations at radio wavelengths reveal synchrotron radiation from electrons spiraling in magnetic fields. Optical observations show emission lines from hot, ionized gas, hydrogen, oxygen, sulfur, glowing in filaments and knots. X-ray observations detect the hottest regions, where temperatures reach millions of degrees. The incident report includes a post-incident monitoring section, with entries tracking the remnant's expansion over decades and centuries. Expansion velocity measured at 8,000 km per second, shell radius increasing, temperature distribution mapped, elemental composition confirmed via spectroscopy. Some of the most famous supernova remnants are centuries old and still visible. The Crab Nebula, the remnant of a supernova observed in the year 1064, has been studied intensively. Its expanding gas shell glows brightly, and at its centre sits a pulsar, a rapidly spinning neutron star that beams radiation toward Earth 30 times per second. The file for that event would note the explosion date, the formation of the pulsar, and ongoing observations of the nebula's structure and evolution. Cassiopeia A, another well-studied remnant, comes from a supernova that exploded around 1670, though it was not recorded by contemporary observers, possibly because interstellar dust blocked the visible light. Its remnant is now a brilliant source of radio and X-ray emission, revealing the complex structure of the ejected material and the presence of a neutron star at the centre. The incident report also documents signals that are more elusive. During a core collapse supernova, the vast majority of the energy, 99% of it, is carried away not by light but by neutrinos. These nearly massless particles flood out of the collapsing core, passing through the overlying layers of the star and into space. Because neutrinos interact so weakly with matter, they escape the star within seconds, carrying direct information about the core collapse itself. On Earth, neutrino detectors, large tanks of water or other materials located deep underground to shield them from cosmic rays, can record a tiny fraction of the neutrinos from a nearby supernova. In 1987, a supernova occurred in the Large Magellanic Cloud, a small galaxy neighbouring the Milky Way, at a distance of about 160,000 light-years. Supernova 1987A was the closest supernova visible to the naked eye since 1604. Hours before the supernova brightened in visible light, neutrino detectors in Japan and the United States recorded a burst of about 24 neutrinos arriving over a period of roughly 10 seconds. This was the first and so far only direct detection of neutrinos from a supernova, and it confirmed theoretical predictions about core collapse. The incident report for that event includes entries for neutrino burst recorded at time t, neutrino count, and energy spectrum consistent with core collapse models. Gravitational waves are another potential signal. When a massive star's core collapses asymmetrically, or when a neutron star forms and wobbles or oscillates, it can generate ripples in spacetime that propagate outward at the speed of light. Gravitational wave detectors like LIGO and Virgo are sensitive enough to detect these signals from supernovas within our galaxy or nearby galaxies. No supernova gravitational wave signal has yet been confirmed, but the infrastructure is in place, and future detections will add another data channel to the incident report. The file anticipates this. Gravitational wave signature pending, detector, sensitivity sufficient for events within 10 megaparsecs, waveform templates prepared for core collapse and neutron star formation scenarios. Supernovas do not occur in isolation. They are violent events that affect their surroundings in profound ways. The expanding shockwave from a supernova compresses nearby clouds of gas and dust, and this compression can trigger the collapse of those clouds into new stars. In this sense, supernovas help to regulate the cycle of star formation in galaxies. The file includes an environmental impact statement, noting that the shockwave from this event will compress gas clouds within 10 to 20 parsecs, potentially initiating star formation in approximately 1 to 2 million years. the same shock also injects energy into the interstellar medium, heating it and stirring it, which can suppress star formation in other regions. Over millions of years, the cumulative effect of many supernovas shapes the structure of galaxies, driving galactic winds, enriching the gas with heavy elements, and influencing where the next generation of stars will form. Astronomers maintain long-term records of supernova events, compiling statistics on their rates, types, and properties. Each supernova discovered is logged with its coordinates on the sky, its type determined from spectroscopy, its host galaxy, its light curve, and any other measurable properties. Over time, these records accumulate into large databases. The rate of core collapse supernovas in a galaxy correlates with the galaxy's star formation rate, since massive stars that explode as supernovas have short lifetimes and die soon after they form. The rate of Type Ia supernovas is more complicated depending on the population of white dwarfs and binary systems, and these events can occur long after star formation has ceased. By studying supernova rates in different types of galaxies and at different distances, meaning different times in the past due to the light travel time, astronomers can trace the history of star formation and chemical enrichment across cosmic time. The incident report for each supernova is one row in a very large, very patient cosmic spreadsheet, each entry contributing to our understanding of how galaxies evolve. From Earth, we observe supernovas as sudden bright points in the sky, or as outbursts in distant galaxies captured by telescopes. By the time we see the light, the core collapse or thermonuclear runaway is already finished. Light from a supernova 1 million light-years away has been travelling for 1 million years before reaching us. We are not witnessing the event in real time. We are reading its aftermath, reconstructing the timeline from its light curve, its spectrum, and the remnant it leaves behind. Our role is that of auditors, examining records after the fact, piecing together what happened from the data that survives. We measure the rise and fall of brightness, the expansion velocity of the ejector, the elements present in the spectrum, and from these clues we infer the nature of the progenitor star, the physics of the explosion, and the fate of the core. Some supernovas are discovered within hours of the explosion, when the shockwave first breaks through the star's surface and the light begins to climb. Others are found days or weeks later, already near peak brightness. A few have been caught early enough that astronomers could point other telescopes at them immediately, capturing the rapid changes in brightness and colour as the expanding fireball evolves. These early observations provide crucial constraints on the size and structure of the progenitor star. Was it a red supergiant with a large diffuse envelope, or a more compact star that had already lost much of its outer layers? The light curve and spectrum hold the answers, and each observation adds another line to the incident file. The peak brightness of a supernova can rival that of an entire galaxy, at least for a few weeks. Then it fades. Within a few months, it becomes too dim for most telescopes to follow. But the remnant continues to expand and shine, visible for thousands of years. Observations of young remnants, a few decades to a few centuries old, show rapidly expanding shells with complex structures. Older remnants, thousands of years old, are larger and fainter, merging gradually with the surrounding interstellar medium. Eventually, after tens of thousands of years, the remnant disperses completely, its material mixed into the gas from which new stars will form. The heavy elements forged in the supernova become ingredients for future planets, and the energy injected by the explosion leaves its mark on the structure of the galaxy. The incident report closes with a summary. A star that once fused hydrogen in stable equilibrium for millions of years exhausted its fuel options, built an iron core that could not be supported and collapsed. The collapse released enough energy to blow the star apart, ejecting its outer layers into space and leaving behind a neutron star or black hole. Or, in the case of a white dwarf, a slow accumulation of mass triggered a thermonuclear runaway that destroyed the star entirely. Either way, the event is now filed under completed, with the remnant and ejector tracked in ongoing monitoring reports. The star is no longer operating. Its materials are now dispersed, its energy released, its final state documented. The file goes on the shelf, labelled with a catalogue number and a date, joining countless others. As you imagine this file closing, you might picture a quiet archive, rows of shelves holding the records of stars that have reached their end. Each file tells a similar story: a long period of stability, a gradual exhaustion of resources, a tipping point where the usual rules no longer apply, and a final transition, sometimes dramatic, always conclusive. These files are not filled with chaos or terror, only with measurements, timestamps, and the calm notation of physical processes playing out according to the laws that govern matter and energy. A supernova is not a tragedy. It is a conclusion, a necessary step in the cycle that allows galaxies to grow, evolve, and produce the complexity we observe today. The explosion that ends one star enriches the medium for the next generation. The compact remnant that remains carries information about extreme physics, probing the limits of density, temperature, and gravity. The light that reaches us, delayed by distance and time, becomes a tool for understanding the universe's expansion and history. Tonight, as the file closes, there is no need for alarm, no call for urgency. The star completed its operating life, filed its final report, and its contents have been distributed into space as inventory for future use. The incident is logged, the data preserved, the outcomes understood. Somewhere in the galaxy, another star is beginning the same slow process, burning hydrogen, building helium, and logging routine entries in its own maintenance file. One day, it too will reach the end of its fuel supply, and its file will record the same sequence of events: core evolution, fuel transitions, loss of support, collapse or explosion, remnant formation, and dispersal. The process is neither good nor bad. It simply is. The universe keeps its records, and we read them when the light arrives, patient auditors of stellar lives that ended long before we were here to notice. The file is closed, the star is done, the paperwork is complete. The next story is about to begin. Please relax and enjoy. Tonight we're not watching supernova montages or dramatic time lapses. We're paging through a standard maintenance manual for an ordinary star. In astrophysics, a star's life can be thought of as a series of scheduled phases: formation, long stable operation, gradual adjustments, and eventual shutdown. Our goal is to quietly follow one typical Sun-like star from its first entry as a cold gas cloud all the way to its retirement as a faint ember in space. The starting point is a cold, dark molecular cloud made of hydrogen, helium, and trace heavier elements drifting in a galaxy's spiral arm. Temperatures are just a few tens of degrees above absolute zero. Motions are slow and subtle. For a long time, nothing happens in a dramatic sense. In the maintenance metaphor, this is the inventory stage, raw material sitting in storage, logged as available but not yet assigned to any specific project. The cloud extends across dozens of light years, a diffuse accumulation of atoms and molecules that have been wandering through interstellar space for millions of years. Some of this material may have been ejected from earlier generations of stars, carrying with it the chemical signature of past fusion processes, but now it simply drifts, dark and nearly motionless against the backdrop of the galaxy. Within this vast reservoir of gas, density varies from place to place. Some regions are slightly more compressed than others, though the differences are subtle. The hydrogen molecules cluster loosely, their thermal energy barely sufficient to resist the weak tug of gravity. At such low temperatures, molecular bonds form more readily, and the cloud contains not just atomic hydrogen, but also molecular hydrogen, along with traces of carbon monoxide, water ice on dust grains, and other simple compounds. These molecules absorb and scatter starlight from distant sources, rendering the cloud opaque to visible wavelengths. From the outside, it appears as a dark patch against the Milky Way, a shadow in space. The dust grains themselves are worth a moment of attention. These microscopic particles, often less than a micrometer across, are composed of silicates, carbon, and ice mantles. They form in the cool atmospheres of evolved stars and are ejected into space by stellar winds. In the cold molecular cloud, they serve as surfaces where molecules can form and as shields that block ultraviolet radiation that might otherwise dissociate those molecules. The dust-to-gas ratio is small, perhaps 1% by mass, but the grains play an outsized role in the cloud's thermal and chemical behavior. They radiate away heat at infrared wavelengths, helping the cloud remain cold. They also help the cloud fragment into smaller, denser clumps by providing additional opacity and altering the local energy balance. For eons, the cloud might remain in this state, a dormant inventory of stellar raw materials. But the galaxy is not a static place. Spiral arms sweep through the disk, compressing gas as they pass. Massive stars elsewhere explode as supernova, sending shockwaves racing through the interstellar medium. Even the gravitational influence of passing molecular clouds can perturb the delicate balance. These disturbances are the small events that trigger a work order. A shock wave from a nearby supernova compresses a portion of the cloud, pushing gas inward. The increased density amplifies the gravitational attraction between particles, and what was once a slow drift becomes a slow infall. Some regions become just dense enough for gravity to start pulling gas inward more strongly than pressure can push it back. This is the work order open moment. A region has been flagged for star formation, though from a distance it still looks quiet and opaque. The triggering mechanism matters less than the result. Whether initiated by a supernova shock, a spiral density wave, or the collision of two clouds, the outcome is the same. A portion of the cloud becomes gravitationally unstable. The condition for this instability is captured in the Jeans criterion, which compares the gravitational potential energy of a gas cloud to its thermal energy. When gravity wins, collapse begins. The critical mass and size depend on temperature and density, but for typical molecular cloud conditions, the collapsing regions have masses ranging from a fraction of a solar mass to several solar masses. Not every part of the cloud collapses. Turbulence and magnetic fields can provide support in some regions, while others fragment into multiple collapsing cores. Star formation is thus a messy, inefficient process, with only a small fraction of the cloud's total mass eventually ending up in stars. Gravity is patient. The initial collapse is gentle, almost imperceptible. Over hundreds of thousands of years, gas streams inward toward the densest point, a region that will become the protostellar core. As material accumulates, the core grows more massive, and its gravitational pull strengthens. The infill accelerates, though still on timescales measured in millennia. The collapsing cloud fragment is not a perfect sphere. It carries angular momentum from the original turbulent motions of the molecular cloud. As gas spirals inward, conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms. The result is a flattened, rotating disk of material surrounding the growing core. This disk will later serve as a reservoir from which the star continues to draw mass, and it may also be the birthplace of planets, though that is another story. The formation of the disk is a critical step. Without it, the collapsing material would simply fall directly onto the core, and the angular momentum would cause the system to spin so fast it would fly apart. The disk allows material to lose angular momentum through viscous processes and magnetic interactions, permitting it to spiral inward gradually. The disk is also a site of complex chemistry. In the cold outer regions, volatile compounds like water, methane, and ammonia freeze onto dust grains, forming ices that will later become incorporated into planets and comets. Closer to the core, where temperatures are higher, only refractory materials like silicates and metals remain solid. This temperature gradient creates a chemical gradient in the disk, with icy bodies forming in the outer regions and rocky bodies in the inner regions. The core itself is hidden deep within an envelope of infalling gas and dust. The immense column density of material makes the region opaque at visible and even infrared wavelengths. Only at longer wavelengths, in the radio and submillimeter bands, can observers detect the warm glow of dust heated by the energy released during gravitational contraction. In the manual, this phase is labelled core assembly and initial compression. No fusion yet, just parts being gently pushed into place by gravity. The core grows denser and hotter as gravitational potential energy is converted into thermal energy. Gas molecules collide more frequently, and the temperature climbs from tens of degrees to hundreds, then thousands of degrees Kelvin. At these higher temperatures, molecules dissociate into atoms, and the gas becomes a plasma of ionized hydrogen and helium. The heating is a direct consequence of compression. When gas falls inward, it accelerates, converting gravitational potential energy into kinetic energy. When it collides with other infalling gas at the core, that kinetic energy is thermalized, converted into random motions of particles, which we perceive as heat. This is the same process that heats the air when you pump up a bicycle tire. The more massive the core becomes, the stronger its gravity, and the more energy is released by infalling material. Eventually, the core becomes hot enough to radiate energy at infrared wavelengths, and it begins to glow, though it remains hidden within its dusty cocoon. The protostar is born from this process, a hot, dense object still shrouded in gas and dust. It radiates energy from gravitational contraction rather than nuclear fusion. The luminosity comes from the release of gravitational potential energy as material continues to fall onto the growing protostellar core. For tens of thousands of years, the protostar remains embedded in its natal cocoon, accreting mass and slowly approaching the conditions necessary for fusion. Outflows and jets may appear along the rotation axis, driven by magnetic fields threading through the disk and core. These jets carry away excess angular momentum and energy, helping to regulate the infall and clear some of the surrounding material. The jets plough into the ambient molecular cloud, creating shockwaves and sometimes carving out cavities visible at infrared wavelengths. In service terms, this is a warm-up test, checking that the core holds together, that energy can escape, and that the system is approaching the temperature and pressure thresholds needed for sustained fusion. The jets are among the most dramatic features of the protostellar phase. They can extend for light years, moving at hundreds of kilometers per second, and they are often visible as bright knots of emission where the jet material collides with the surrounding gas. The mechanism that launches these jets is still a topic of active research, but it likely involves magnetic fields anchored in the disk and twisted by the rotation. The magnetic field lines act like a spinning garden hose, flinging material outward along the rotation axis. Some of this material escapes entirely, while some falls back onto the disk farther out. The jets are episodic, turning on and off as the accretion rate varies, and they leave behind a trail of shocked gas that gradually fades as it cools and disperses. Eventually, the protostar gathers enough mass that its core temperature and density climb high enough for a new process to begin. Deep in the center, where temperatures reach several million degrees Kelvin and pressures are immense, hydrogen nuclei, protons, begin to overcome their mutual electrostatic repulsion and fuse together. The fusion proceeds through the proton-proton chain, a sequence of nuclear reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus, releasing energy in the form of gamma-ray photons and neutrinos. The energy generated by fusion diffuses outward through the star, taking hundreds of thousands of years to work its way from the core to the surface, where it is finally radiated into space as visible light. Once the inward pull of gravity is balanced by the outward pressure from fusion-generated energy, the star reaches hydrostatic equilibrium. This marks the start of the main sequence phase. The manual records this as primary power engaged and system in stable operation, the longest, most uneventful part of the schedule. The transition to the main sequence is not instantaneous. The protostar must first clear away its surrounding envelope, a process that can take a few million years. Strong stellar winds driven by the star's radiation pressure and magnetic activity blow away the remaining gas and dust. The disk gradually dissipates, either accreted onto the star, blown away by winds, or incorporated into planets. The star emerges from its cocoon, now visible at optical wavelengths, and settles onto the main sequence. For a sun-like star, this entire formation process, from the initial collapse of the molecular cloud to the establishment of stable hydrogen burning, takes about 50 million years, a blink of an eye in cosmic terms, yet far longer than all of human history. The main sequence is a long plateau of stability. For billions of years, the star quietly converts hydrogen into helium in its core, radiating a nearly constant amount of energy. Its radius and temperature change only slowly. From the outside, this is simply a yellow star shining in the sky, doing its job. The star settles into a routine governed by well-understood physics. Gravity compresses, fusion heats, pressure resists, and radiation carries energy away. In the maintenance log, routine checks would show the same readings over and over. Core temperature within range, luminosity stable, fuel consumption steady. The star's surface temperature hovers around 5,800 degrees Kelvin, its radius roughly 700,000 kilometers, its luminosity a steady output of nearly 4 times 10 to the 26th watts. These parameters define a G-type main sequence star, a common variety in the galaxy. Life on any orbiting planets, if such exist, can rely on this stability. The star's output changes by less than 1% over millions of years, providing a consistent energy source. Photons stream outward, carrying energy produced by fusion reactions that occurred deep in the core long ago. The photosphere, the visible surface, is a roiling layer of convecting plasma where hot gas rises and cool gas sinks, creating a granular pattern visible through telescopes. Above the photosphere lies the chromosphere and the corona, tenuous outer layers heated by magnetic activity and shockwaves. The star may have a magnetic field generated by dynamo processes in its interior, leading to phenomena like sunspots, flares, and coronal mass ejections. But these are surface details, minor disturbances in the otherwise steady operation. The internal structure of a main sequence star like our Sun is layered like an onion. At the centre is the core, where fusion occurs. This region extends to about a quarter of the star's radius, but contains over half its mass and nearly all the energy generation. The temperature in the core is around 15 million degrees Kelvin, and the density is roughly 150 times that of water, hot enough and dense enough for protons to fuse despite their electrostatic repulsion. Above the core is the radiative zone, where energy is transported outward primarily by radiation. Photons are repeatedly absorbed and re-emitted by atoms, diffusing slowly outward in a random walk that takes hundreds of thousands of years. The outer third of the star, by radius, is the convective zone, where energy is transported by bulk motions of gas. Hot plasma rises to the surface, cools by radiating energy into space and then sinks back down to be reheated. This convection is what creates the granular pattern seen on the Sun's surface and drives the magnetic dynamo that powers solar activity. Even during the main sequence, small changes accumulate. Helium builds up in the core, altering its composition and density. Because helium nuclei are heavier than hydrogen and do not fuse at the temperatures prevailing in the core during this phase, helium accumulates like ash in a slow-burning fire. As the helium fraction increases, the core must contract slightly and heat up to maintain the pressure needed to support the overlying layers. This causes the fusion rate to increase slightly, which in turn causes the star to become gradually more luminous. Over billions of years, the star's luminosity may increase by tens of %. Its radius also expands slightly, and its surface temperature adjusts. These adjustments are gentle and stretched over immense timescales. In the manual, they would appear as infrequent updates to configuration values. Core helium fraction increased and radius slightly expanded without any flagged alarms. The slow brightening of a main sequence star has profound implications for any planets in its habitable zone. The region where temperatures are suitable for liquid water. A planet that starts out in the habitable zone may eventually become too hot as the star brightens, while a planet that is initially too cold may warm up and become habitable later in the star's life. For Earth, the Sun's luminosity has increased by about 30% since it formed 4.5 billion years ago. This increase would have been catastrophic for early life, if not for feedback mechanisms in Earth's climate system, such as changes in atmospheric composition and cloud cover that have kept the planet's temperature relatively stable. But eventually, perhaps a billion years from now, the Sun will become too bright for Earth to remain habitable, and the oceans will evaporate. For a Sun-like star, the main sequence lasts approximately 10 billion years. During this time, the star burns through roughly 10% of its total hydrogen supply. The hydrogen in the core, where temperatures and densities are high enough for fusion. The hydrogen in the outer layers remains untouched, too cool and diffuse to participate in nuclear reactions. Eventually, the hydrogen in the core becomes significantly depleted. The fusion rate drops, and the energy generation in the core can no longer sustain the same equilibrium. Without sufficient thermal pressure to counterbalance gravity, the core begins to contract under its own gravity. As it contracts, gravitational potential energy is converted into heat, raising the core temperature. This higher temperature ignites hydrogen fusion in a shell surrounding the inert helium core. The shell-burning region produces energy at a higher rate than the core did during the main sequence. The star's outer layers respond to these core changes. The increased energy output from the hydrogen-burning shell pushes the envelope outward. The star's radius begins to increase, and as it expands, the surface temperature drops because the same luminosity is now spread over a much larger area. In service language, this is the first major notice. Primary fuel region nearing end of specification, prompting the system to shift into a new operating mode. The star enters the subgiant phase, a transitional period bridging the main sequence and the red giant branch. The changes occur over tens of millions of years, slow by human standards, but rapid compared to the billion-year main sequence. During the subgiant phase, the star's structure becomes more complex. The inert helium core continues to contract and heat, while the hydrogen-burning shell steadily works its way outward through layers of previously unburned hydrogen. The envelope expands, but not yet to the extreme radii characteristic of red giants. The star's position on the Hertzsprung-Russell diagram, a plot of luminosity versus temperature used by astronomers to classify stars, traces a path upward and to the right, away from the main sequence. Observationally, subgiants are less common than main sequence stars simply because they spend less time in this phase, but they are not rare. Many bright stars visible to the naked eye, such as Procyon, are subgiants. The red giant expansion is a configuration change in the outer layers. As the core continues to contract and heat up, the shell-burning region becomes increasingly energetic. The envelope expands dramatically, swelling to tens or even hundreds of times its main sequence radius. The surface cools to around 3,000 or 4,000 degrees Kelvin, shifting the star's colour from yellow to orange or red. The star becomes a red giant, larger in radius, cooler at the surface, and more luminous overall. This might sound dramatic, but in the manual it's filed as a configuration change. Radius parameter increased, surface temperature decreased, luminosity updated. The internal engine remains governed by the same physics, just with new settings. The outer envelope becomes so extended that gravity at the surface is weak, and the star begins to lose mass through a slow, steady stellar wind. Gas drifts away from the surface, enriching the surrounding interstellar medium with processed material. The scale of a red giant is difficult to grasp. If our Sun were to become a red giant, as it will in about 5 billion years, its surface would extend beyond the orbit of Mercury, possibly even beyond Venus. Earth, if it survives, would be subjected to intense heating and tidal forces. The star's luminosity would increase by thousands of times, and any remaining atmosphere on Earth would be stripped away. The outer layers of the star, meanwhile, would be tenuous, with densities far lower than the best laboratory vacuums. An observer could, in principle, pass through the outer envelope of a red giant without encountering much resistance, though the intense radiation would make it inadvisable. The inert helium core, meanwhile, continues to contract and heat. Electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, begins to provide significant support against further collapse. In degenerate matter, pressure depends on density rather than temperature, which has important consequences for what happens next. For a Sun-like star, the contracting core eventually reaches a temperature around 100 million degrees Kelvin, hot enough for helium nuclei to begin fusing. Helium fusion proceeds through the triple alpha process. 2 helium nuclei fuse to form an unstable beryllium nucleus, which then captures another helium nucleus to form carbon. Subsequent reactions can build heavier elements like oxygen. Because the core is partially degenerate, the ignition of helium fusion can occur abruptly in what is called a helium flash. The flash releases an enormous amount of energy in a short time, but most of it goes into lifting the degeneracy, heating the core and reducing its density, rather than being radiated away. The envelope barely notices. Within hours or days, the core adjusts to a new equilibrium with stable helium fusion. The helium flash is one of the more peculiar events in stellar evolution. Because the core is degenerate, the usual thermostatic controls that regulate fusion do not apply. In a normal, non-degenerate star, an increase in fusion rate heats the gas, causing it to expand and cool, which reduces the fusion rate, a negative feedback loop that keeps fusion stable. In a degenerate core, however, an increase in fusion rate does not immediately cause the pressure to increase, because the pressure is determined by density, not temperature. The fusion rate can therefore run away, increasing exponentially. For a brief period, the helium-burning core of a Sun-like star can reach luminosities equivalent to the entire luminosity of the Milky Way galaxy. But this energy is absorbed by the overlying layers, which expand and lift the degeneracy. Once the core becomes non-degenerate again, normal thermostatic controls take over, and the fusion rate stabilizes. The entire event lasts only a few seconds at its peak, though the core takes several thousand years to fully settle into stable helium burning. The maintenance log records secondary fuel cycle initiated, helium fusion in core, marking a midlife upgrade of the fusion system. The star now burns helium in its core and hydrogen in a surrounding shell. This configuration is more stable than the shell-burning only phase, and the star settles onto the horizontal branch, a phase of stable helium burning that lasts around 100 million years. The star's luminosity and radius are roughly constant during this time, though somewhat higher than during the main sequence. It is a brief respite, a period of stable operation before the next series of adjustments. The horizontal branch phase is named for the star's position on the Hertzsprung-Russell diagram, where stars in this phase occupy a roughly horizontal band. The exact position depends on the star's mass and composition, particularly the abundance of heavier elements. Stars with lower metallicity, fewer elements heavier than helium, tend to be hotter and bluer on the horizontal branch, while those with higher metallicity are cooler and redder. Globular clusters, which contain old, metal-poor stars, often show well-defined horizontal branches, making them useful for studying stellar evolution and determining the ages of star clusters. Eventually, the helium in the core is significantly consumed, leaving behind a core of carbon and oxygen. Once again, fusion in the core cannot be sustained, and the core contracts. Helium now burns in a shell around the inert carbon-oxygen core, and hydrogen continues to burn in a shell outside the helium-burning shell. The star enters a phase of double shell burning, a more complex configuration that can lead to structural instabilities. The two burning shells do not always operate smoothly in tandem. The helium shell, in particular, can experience thermal pulses, periodic episodes of intense burning followed by quiescence. During a pulse, the helium shell ignites vigorously, releasing a surge of energy that drives convection and temporarily disrupts the hydrogen shell. The star's luminosity and radius fluctuate in response. These thermal pulses, also known as helium shell flashes, occur every few thousand to tens of thousands of years. During a pulse, the helium-burning shell can briefly become more luminous than the entire rest of the star. The pulse drives convection that reaches deep into the interior, dredging up freshly synthesized carbon and other elements and mixing them into the envelope. This process, called third dredge-up, enriches the envelope with carbon, and if enough dredge-up episodes occur, the star can become carbon-rich, with more carbon than oxygen in its atmosphere. Such stars are called carbon stars, and they are characterized by distinctive spectral features and deep red colors. The carbon condenses into soot particles in the cool outer atmosphere, making these stars important sources of dust in the galaxy. This phase is complex but manageable. In the service manual, multiple active zones are listed with their respective temperatures and fuel types, still governed by the same conservation laws and nuclear reactions. The star may experience pulsations, periodic variations in brightness and size as it oscillates between different equilibrium states. Some stars in this phase become long-period variables, with brightness changes detectable over months or years. The extended envelope, now reaching far from the core, is loosely bound. Strong stellar winds, driven by radiation pressure on dust grains forming in the cool outer layers, carry away significant amounts of mass. The star sheds a substantial fraction of its envelope, perhaps half its total mass or more, over a few 100,000 years. The mass loss is a critical part of the star's evolution. Without it, the star would continue to expand and contract through thermal pulses indefinitely. But the stellar wind gradually removes the envelope layer by layer until only the core and inner shells remain. The wind is strongest when the star is brightest and coolest, during the peaks of its pulsation cycles. Dust grains form in the cool, dense gas above the photosphere, and radiation pressure on these grains drives the wind outward at speeds of 10 to 20 kilometers per second. The wind carries away not just mass but also angular momentum, and it enriches the interstellar medium with carbon, nitrogen, oxygen, and other elements synthesized in the star's interior. The ejected material forms a diffuse shell of gas and dust around the star. To an observer, this may eventually appear as a planetary nebula. Despite the misleading name, these objects have nothing to do with planets, but were named for their round, planet-like appearance in early telescopes. In our quiet framing, it is simply the star discarding outer components that are no longer needed. The logbook notes envelope mass reduced and outer layers detached for recycling into the interstellar medium. The nebula glows as ultraviolet radiation from the hot exposed core ionizes the ejected gas. Planetary nebulae are among the most beautiful objects in the sky, with intricate shapes sculpted by stellar winds, magnetic fields, and interactions with the interstellar medium. But from the star's perspective, this is a maintenance procedure. removing unnecessary mass to expose the core for final shutdown. Planetary nebulae display an astonishing variety of shapes. Some are nearly spherical, others have bipolar lobes, still others show complex multi-shell structures. The shapes are thought to arise from the interaction between fast winds from the central star and slower winds ejected earlier, combined with effects from binary companions' rotation and magnetic fields. The nebulae are transient, lasting only tens of thousands of years before dispersing into the interstellar medium. During this time, they are illuminated by the hot central star, which can have surface temperatures exceeding 100,000 degrees Kelvin. The ionized gas glows in characteristic emission lines: hydrogen, oxygen, nitrogen, each producing a different color. Images of planetary nebulae often show vibrant reds, greens, and blues, a visual record of the star's chemical legacy. What remains after the envelope is shed is a hot, dense core, a white dwarf, composed mostly of carbon and oxygen. Fusion has effectively ceased. The white dwarf shines from residual heat, slowly cooling over time. It is supported against gravity by electron degeneracy pressure rather than thermal pressure from fusion. In the maintenance metaphor, this is decommissioned but still warm hardware. Active fusion channel closed, system in passive cooling mode. The white dwarf is extraordinarily dense, packing roughly half the Sun's mass into an object about the size of Earth. A teaspoon of white dwarf material would weigh several tons. The surface temperature can be as high as 100,000 degrees Kelvin initially, making the white dwarf a brilliant source of ultraviolet light. But there is no internal energy source, only the stored thermal energy left over from the fusion phases. The physics of white dwarfs is governed by quantum mechanics. The electrons in the dense core are packed so tightly that they obey the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state. This creates a pressure, electron degeneracy pressure, that depends only on density, not temperature. As a result, a white dwarf can support itself against gravity even after it cools and stops radiating. There is a limit, however, to how massive a white dwarf can be. The Chandrasekhar limit, around 1.4 solar masses, is the maximum mass that electron degeneracy pressure can support. If a white dwarf accretes mass from a companion star and exceeds this limit, it will collapse, likely triggering a thermonuclear explosion known as a Type Ia supernova. Over billions of years, the white dwarf radiates away its stored thermal energy, becoming dimmer and cooler. The cooling is slow because the white dwarf's small surface area limits the rate at which energy can be radiated. The surface temperature drops from tens of thousands of degrees to thousands, then hundreds. The color shifts from blue-white to white, then to red, and eventually the white dwarf would become too faint to see at visible wavelengths. In theory, given enough time, it would cool to a black dwarf, an inert, cold lump of carbon and oxygen with a temperature close to that of the cosmic microwave background. However, the universe is not yet old enough for any white dwarf to have cooled to this state. The oldest white dwarfs, formed in the early history of the galaxy, are still radiating faintly in the infrared. In the log, this final phase is just a slowly declining temperature trace. No new processes, no major events, only quiet, asymptotic cooling. The white dwarf will persist in this state effectively forever, a stable remnant that will outlast almost everything else in the galaxy. It is the final entry in the service manual for a sun-like star, a quiet endpoint, a small ember in the dark. The gas and dust expelled during the red giant and planetary nebula phases are not lost. They enrich the interstellar medium with heavier elements like carbon, nitrogen, and oxygen, elements that were forged in the star's interior through nuclear fusion. Over time, these materials mix with the ambient gas and can become part of new molecular clouds, new stars, and new planets. The carbon in your body, the oxygen you breathe, the nitrogen in your DNA, all were produced inside stars and returned to space when those stars shed their envelopes. From the maintenance perspective, unused or worn components are returned to the warehouse shelves, available for future projects in the Galactic Workshop. The cycle continues, with each generation of stars building on the chemical legacy of the previous one. This process of chemical enrichment has been ongoing for billions of years, gradually increasing the abundance of heavy elements in the galaxy. The first stars, formed from the primordial gas left over from the Big Bang, contained only hydrogen and helium, with trace amounts of lithium. These stars, known as population 3 stars, were likely very massive and short-lived. When they exploded as supernovae, they seeded the interstellar medium with the first heavy elements. Subsequent generations of stars formed from this enriched gas contained progressively more heavy elements, a trend that continues to the present day. Our Sun, formed about 4.5 billion years ago, is relatively metal-rich compared to older stars, reflecting the cumulative enrichment from billions of years of stellar evolution. It is important to note that the schedule described applies to a typical Sun-like star with a mass around 1 solar mass. More massive stars have more compressed schedules and more dramatic end-of-life events. Stars more than about 8 times the mass of the Sun burn through their fuel much faster, exhausting their hydrogen in just tens of millions of years rather than billions. Their cores are hot enough to fuse carbon and oxygen into even heavier elements: neon, magnesium, silicon, iron. When such a star exhausts its nuclear fuel, its core collapses catastrophically in a core collapse supernova, an explosion so bright it can briefly outshine an entire galaxy. The core may be crushed into a neutron star, an object even denser than a white dwarf, or if the core is massive enough, it may collapse entirely into a black hole. Low-mass stars, on the other hand, burn fuel so slowly that they outlive the current age of the universe. A red dwarf with a tenth. The mass of the Sun might have a main sequence lifetime of trillions of years. These stars are fully convective, mixing their interiors and allowing them to burn through a much larger fraction of their hydrogen. When they eventually exhaust their fuel, they may transition directly to a helium white dwarf without ever becoming a red giant, though this remains theoretical since no red dwarf has yet had time to complete its life cycle. Each mass range has its own version of the manual, with different pages for final outcomes, but the core steps, formation, main sequence operation, fuel changes and final remnants, are shared across the stellar population. The timescales involved are enormous, beyond easy human comprehension. Star formation, from the initial compression of a molecular cloud to the ignition of fusion, takes hundreds of thousands to a few million years. The main sequence lifetime of a Sun-like star is around 10 billion years, more than twice the current age of the Earth, more than 2/3 the age of the universe itself. Post-main sequence phases, subgiant red giant horizontal branch, asymptotic giant branch, add another few hundred million years. The white dwarf cooling phase extends for tens of billions of years, far longer than the universe has existed so far. In human terms, the maintenance intervals are unimaginably long. The service manual is more of a geologic and cosmic record than a routine checklist, entries spaced so widely that entire civilizations could rise and fall between them. And yet, for all these vast stretches of time, the life of a star is orderly and predictable. The same physical laws govern every stage: gravity, thermodynamics, nuclear physics, quantum mechanics. There are no surprises, no improvisations, just a long sequence of phases that stars across the galaxy quietly follow. Astronomers can observe stars at every stage of this sequence, from the cold molecular clouds where stars are just beginning to form, to the bright main sequence stars like our Sun, to the swollen red giants, to the faint white dwarfs cooling in the dark. By studying populations of stars at different stages, we can piece together the entire life cycle, even though no single star completes it within a human lifetime, or even within the entire span of recorded history. The observational evidence for stellar evolution is overwhelming. Astronomers have catalogued millions of stars, measuring their temperatures, luminosities, compositions, and ages. When these measurements are plotted on a Hertzsprung-Russell diagram, distinct patterns emerge: a main sequence where most stars reside, a red giant branch where stars expand and cool, a horizontal branch where helium-burning stars cluster, and a region where white dwarfs slowly fade. These patterns match the predictions of stellar evolution models with remarkable precision. The models, which solve the equations of stellar structure under various conditions, reproduce not only the overall evolutionary path, but also details like pulsation periods, mass loss rates, and nuclear synthesis yields. One of the most powerful tests of stellar evolution theory comes from star clusters. Clusters are groups of stars that formed at roughly the same time from the same molecular cloud, so they all have the same age and initial composition. The only significant difference among cluster members is their mass. By observing a cluster, astronomers can see stars at different evolutionary stages, all corresponding to the same age. Young clusters, a few million years old, contain many massive luminous main sequence stars and no red giants or white dwarfs. The massive stars have not yet had time to evolve. Intermediate age clusters contain main sequence stars, red giants, and perhaps some white dwarfs. Stars more massive than a few solar masses have evolved off the main sequence. Old clusters, billions of years old, have no massive main sequence stars left, only low-mass main sequence stars, red giants, horizontal branch stars, and many white dwarfs. The oldest globular clusters, some over 12 billion years old, provide snapshots of stellar evolution over nearly the entire age of the universe. The story of a star is, in many ways, the story of order emerging from chaos. A diffuse, turbulent cloud of gas, stirred by galactic dynamics and the violence of supernovae, gradually collapses under its own gravity. What begins as a disordered collection of atoms becomes a tightly organized, stable fusion reactor, governed by the balance between gravity and pressure. For billions of years, the star maintains this balance with remarkable precision, its internal structure adjusting automatically to changes in composition and energy generation. Even as it exhausts one fuel source and transitions to another, the underlying principles remain the same. Gravity compresses, fusion resists, energy flows outward, and the star persists. When the fuel finally runs out, the star does not explode or vanish. It simply settles into a new state, a dense remnant supported by quantum pressure, cooling slowly over eons. The material it sheds enriches the galaxy, contributing to the next generation of stars and planets. In this way, stars are not isolated objects, but participants in a vast cycle of matter and energy that has been ongoing for billions of years. The atoms that make up the Earth and everything on it have passed through this cycle multiple times, forged in the cores of ancient stars, expelled into space and gathered again into new molecular clouds. There is a kind of poetry in this, a quiet dignity in the life of a star. It does not rage or struggle. It simply follows the path laid out by physics, phase by phase, adjustment by adjustment, until it reaches its final state. There is no rush, no urgency, only the slow unfolding of processes governed by fundamental laws, and in that unfolding there is a profound stability, a constancy that spans billions of years and trillions of kilometers. The constancy is not absolute, of course. Stars do vary, they do evolve, they do eventually die. But the variations are slow and predictable, governed by equations that can be written on a page and solved with sufficient computational power. The evolution follows a script, and while the details may differ from star to star depending on mass and composition, the broad outlines are universal. Every star that has ever formed, and every star that ever will form, follows the same basic pattern: gravitational collapse, fusion ignition, stable burning, fuel depletion, structural readjustment, mass loss, and final cooling. This universality is one of the great triumphs of astrophysics, a testament to the power of physical law to explain the cosmos. As the listener drifts off, they can imagine shelves of service manuals in a cosmic workshop, each one documenting the slow, methodical life story of a star. Assembled from a cloud, run steadily for eons, gently altered as fuel runs low, and finally retired as a small cooling ember in the dark. Somewhere in the galaxy, a new molecular cloud is beginning to collapse, flagged for star formation. Somewhere else, an ancient white dwarf continues its long fade into invisibility, and in between, billions of stars shine steadily on the main sequence, converting hydrogen into helium, day after day, year after year, for billions of years. The galaxy is filled with these quiet, patient engines, each one following its schedule, each one a small miracle of physics and time. Our star, the one we have followed through this manual, is one among hundreds of billions in the Milky Way alone. It is neither the largest nor the smallest, neither the brightest nor the dimmest. It is ordinary, typical, unremarkable, except for the fact that it exists at all, that it burns steadily for billions of years, that it follows a predictable path from cloud to ember. In its ordinariness lies its significance. This is how stars work. This is the schedule they follow. This is the service manual for a universe that, for all its vastness and complexity, operates according to comprehensible rules, and so we close the manual. The star's life, from cloud to quiet ember, follows a predictable schedule governed by gravity, nuclear physics, and thermodynamics. There is no rush and no improvisation, just a long sequence of phases that stars across the galaxy quietly follow. The work order has been completed, the system decommissioned, the components returned to inventory. Another star, somewhere, is just beginning its journey. The cosmic workshop continues its work, assembling stars from clouds, running them for eons and eventually retiring them as embers. The process has been ongoing for billions of years, and it will continue for billions more, a slow, patient rhythm underlying the life of the galaxy. Tonight, we rest in the knowledge that the stars too follow a schedule, one that stretches across unimaginable spans of time, but a schedule nonetheless, documented in the quiet pages of a maintenance manual filed away in the vastness of space. The next story is about to begin. Please relax and enjoy. Tonight we're not chasing dramatic rain footage or studying satellite loops of swirling storms. We're doing something quieter, opening an attendance sheet for the atmosphere. The monsoon isn't about non-stop downpours or apocalyptic flooding, though those things can happen. It's about a seasonal reversal of winds, a shift in where rising air and rain prefer to gather, a predictable reorganization of pressure patterns that happens year after year. Each monsoon simply clocks in and clocks out. Pressure patterns adjust, winds reorganize, and humid air starts showing up more often, over land instead of lingering over the ocean. It's a routine event in the planet's calendar, documented and logged like any other recurring appointment. The attendance book starts with a simple observation. Land and ocean don't respond to sunlight in the same way. This uneven heating becomes the first line item in understanding how monsoons form. Land heats up quickly when the sun shines on it. Dark soil, rocky surfaces, bare ground, they all absorb solar radiation efficiently and warm the air directly above them. When the sun sets, or the season changes, that same land cools down just as fast, radiating heat back into space. The ocean, by contrast, is a more patient participant. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature even a little. Sunlight penetrates deeper into the ocean, spreading warmth through a thicker layer rather than concentrating it at the surface. The result is that oceans warm slowly and cool slowly, maintaining relatively stable temperatures across the seasons. In the pre-monsoon months, strong sunshine beats down on large continental areas, especially in the subtropics and tropics. Places like the Indian subcontinent, the Tibetan Plateau, the interior of West Africa, and the high deserts of North America absorb that sunlight and turn into enormous heat sources. The ground gets hot, the air above it gets hot, and pressure begins to drop. Meanwhile, the adjacent oceans remain cooler, and their pressure stays higher. In the attendance metaphor, heated land is the first box to get a check mark. The system is beginning to wake up. Air doesn't sit still when pressure differences develop. It moves from regions of higher pressure toward regions of lower pressure, always trying to smooth out imbalances. As land heats and pressure over continents drops, while pressure over adjacent oceans stays higher, a horizontal pressure gradient forms. This gradient isn't a sudden jolt or a violent push. It's a gentle, large-scale rearrangement of where air prefers to flow. The stronger the heating, the stronger the gradient. The stronger the gradient, the more insistent the push from ocean toward land. On the attendance sheet, the pressure difference column gets a quiet tick. The setup is complete, and now the flow can begin. Before the monsoon arrives, prevailing low-level winds might flow from land toward ocean, or they might run parallel to the coastline, depending on the season and the region. In South Asia, for example, the wintertime winds are dry northeasterlies that blow from the cold interior of the continent out toward the warmer Indian Ocean. In West Africa, the dry season features winds from the Sahara pushing southward. But as the pressure gradient builds with the coming of summer, those winds gradually reverse. They don't flip overnight. The transition takes weeks. But once it happens, the new pattern is unmistakable. Moist onshore flows replace the dry continental breezes. In South Asia, the winds turn from dry northeasterlies in winter to moist southwesterlies in summer. This change is like employees switching shifts on a schedule. One flow checks out, the opposite direction checks in. The attendance log notes the reversal, and the monsoon season is officially underway. The ocean is a huge reservoir of moisture, and when winds start blowing from sea to land, they carry water vapor inland. This is the raw material for clouds and rain. As the air travels over warm surfaces and encounters rising terrain, mountain ranges, plateaus, escarpments, it lifts, cools, and condenses. The moisture that was invisible as vapor becomes visible as clouds. In the attendance book, moisture is a separate column. Once the onshore flow has enough length and warmth, once it's been blowing steadily for days or weeks, the humidity box is considered present. The system now has fuel. Heated land doesn't just lower surface pressure, it also makes the air above it buoyant. Each day, especially in the afternoon when the sun is strongest, parcels of warm air rise from the surface. As they rise, they cool, and if they contain enough moisture, that moisture condenses into clouds. This daily convection is a routine process, happening over and over again throughout the monsoon season. With the monsoon moisture supply in place, these daily convection cycles become more frequent and more organised. The pattern is predictable. Sun heats land, air rises, clouds build, showers and thunderstorms form, rain falls, and then the storms decay as the sun sets and the surface cools. The logbook records this as a repeated daily attendance of afternoon convection. It's not chaotic, it's rhythmic. Within the larger monsoon pattern, there are features that help organise the storms. Monsoon troughs are elongated regions of low pressure that form over heated continents and nearby seas. These troughs act like organisational lines on the attendance sheet, gathering storms and enhancing the convergence of moist air. Rather than isolated thunderstorms popping up randomly across the landscape, the monsoon season features recurrent bands and clusters of clouds that line up along these troughs. The trough might sit in roughly the same position for days at a time, or it might shift slowly north or south as the season progresses. Either way, it provides a framework. The sheet now has an entry for organised low-pressure zone present. Storms know where to gather. Monsoon rainfall isn't just about surface winds and rising air, upper-level winds matter too. When air rises from the surface, it has to go somewhere. If the winds aloft are favourable, the rising air can spread out and escape horizontally, a process called divergence. This upper-level divergence creates a kind of vacuum that allows more air to rise from below, strengthening and sustaining the updrafts. If the upper-level winds aren't cooperative, if they block or suppress the outflow, then rising air gets capped and convection weakens. This upper-level pattern acts like support staff, clearing space for new rising air to keep moving upward. On the log, a separate row tracks upper-level support. When it's present, convection has an easier time maintaining itself, and the monsoon rains are more robust. When it's absent, the system sputters. The South Asian monsoon is one of the most well-known examples, a classic tab in the attendance book. Pre-monsoon heating over the Indian subcontinent and the vast Tibetan plateau lowers surface pressure dramatically. The plateau, sitting at high elevation, acts like a huge elevated heat source, amplifying the thermal contrast. Moist air from the Arabian Sea and the Bay of Bengal flows inland as the low-level winds flip from northeasterlies to southwesterlies. The season progresses from south to north, with onset typically beginning along the southwestern coast of India in late May or early June, and then advancing northward over the following weeks. Withdrawal happens in reverse, starting in the northwest in September and retreating southward through October and November. In the file cabinet, this system has its own tab with expected arrival dates, typical progression maps, average rainfall totals, and year-by-year comparisons. The South Asian monsoon is so regular and so well documented that its onset and withdrawal are major events in the regional calendar, affecting billions of people. The West African monsoon involves a similar seasonal shift, but with its own regional character. Here, the Intertropical Convergence Zone, the ITCZ, a belt of low pressure and rising air that circles the planet near the equator, shifts northward over the African continent during the boreal summer. Moist southwesterly winds from the Gulf of Guinea move inland, feeding lines of thunderstorms and organised squall lines that march across the Sahel. As the ITZ migrates north, the region of frequent rain also shifts. Farmers and communities track this movement closely because it determines where and when the rains will arrive. On the attendance sheet, this system's tab shows a moving band of present rain days that tracks north in June and July, reaches its northernmost position in August, and then retreats south through September and October. The pattern is less intense than the South Asian monsoon in some ways, but just as vital to the people who depend on it. The North American monsoon is a more modest but very real pattern affecting parts of Mexico and the southwestern United States. Summer heating over the high deserts, the Mexican plateau, and the basin and range region helps draw moist air from the Pacific Ocean, the Gulf of California, and even the Gulf of Mexico. The result is a seasonal increase in thunderstorms, especially in the afternoons and evenings, across Arizona, New Mexico, and northern Mexico. These storms bring welcome relief from the intense heat and provide a significant portion of the region's annual rainfall. Though less intense and less extensive than some other monsoons, the North American monsoon follows the same checklist: heated land, change pressure patterns, onshore flow, and daily convection. It gets a smaller but very real attendance tab in the binder, with entries noting typical onset in early July and withdrawal by mid-September. Even once the large-scale monsoon pattern is established, storms often follow a regular diurnal cycle, a daily rhythm of building and decay. This is the monsoon clocking in each afternoon and clocking out at night. Morning hours are often quiet with partly cloudy skies and light winds. As the sun climbs higher and surface temperatures rise, convection begins to fire. By early to mid-afternoon, towering cumulus clouds dot the landscape and thunderstorms develop. These storms can produce heavy rain, lightning, gusty winds, and sometimes hail. As evening approaches and the sun sets, the surface cools, convection weakens, and the storms dissipate. Some storms propagate into the night as organized systems, but many simply fade away. From a logging perspective, the large-scale monsoon is a multi-month presence, but its rainfall often occurs in these predictable daily shifts. Each day's entries show similar patterns. Afternoon storms, present again. It's a recurring appointment kept reliably day after day. The monsoon doesn't last forever. As seasons change and the angle and intensity of sunlight decrease, the whole system begins to withdraw. Land surfaces cool more quickly than the ocean, weakening the pressure differences that drove the onshore flow. The thermal gradient that powered the monsoon reverses or disappears. Low-level winds gradually lose their moisture-laden inland direction and revert toward winter patterns. Dry air begins to dominate again. The attendance sheet begins marking early departures. Fewer rainy days appear in the log. The monsoon troughs weaken and shift. More frequent dry spells interrupt the pattern. Finally, the system returns to its off-season routine. Dry winds, stable conditions, and the oceanic moisture source cut off from the land. The monsoon has clocked out, leaving behind another column of data in the long record. The file is updated, the totals are calculated, and the system waits for the next cycle to begin. Monsoon seasons can vary significantly from year to year. This interannual variability is carefully tracked and studied. Some years show stronger pressure gradients and more abundant moisture transport, leading to above-average rainfall. Other years are weaker, delayed, or cut short, resulting in below-average totals and potential drought. Large-scale climate patterns play a role in these differences. El Niño, a warming of the central and eastern tropical Pacific Ocean, tends to weaken monsoons in some regions, such as South Asia, by altering atmospheric circulation patterns and shifting the location of rising air. La Niña, the opposite phase with cooler-than-average Pacific waters, often enhances monsoons in those same regions. Other factors, like the temperature of the Indian Ocean, the strength of high-altitude jet streams, and even distant weather patterns over the Atlantic or the polar regions, can influence monsoon performance. In the attendance metaphor, some years the monsoon is early and diligent, arriving on time and delivering abundant rain. Some years it's late, with onset delayed by weeks. Some years it's quiet, with weak circulation and disappointing totals. Climatologists keep long records of these variations, noting the anomalies and searching for patterns that might improve forecasts. Monsoon behaviour is tracked using a wide array of tools and measurements. Rain gauges scattered across the landscape provide ground truth, recording daily and seasonal totals at thousands of locations. Wind measurements from surface stations and weather balloons capture the reversal of flow and the strength of the onshore currents. Satellite observations provide a broader view, monitoring cloud cover, rainfall estimates, sea surface temperatures, and atmospheric moisture content. All of this data is summarized into indices, numerical values that capture the state of the monsoon at any given time. These data sets form a long historical attendance sheet showing onset dates, total rainfall, spatial patterns, and year-to-year variability. Scientists use these logs to study trends, understand the physical mechanisms at work, and refine seasonal forecasts. The file cabinet grows thicker over time, but the format remains familiar: dates, totals, anomalies, and quiet notes about what happened and why. For many regions, monsoon rains are essential for agriculture, reservoirs, and groundwater recharge. Too little rain can mean drought, crop failure, water shortages, and economic hardship. Too much rain can mean flooding, landslides, and damage to infrastructure. Yet in this story, we keep the focus on the pattern rather than the disasters. Monsoons are scheduled deliveries of water that communities have adapted to over centuries. Farmers time their planting to the monsoon's arrival. Water managers plan reservoir operations around expected seasonal inflows. Cities and villages have developed strategies for coping with both the abundance and the absence of rain. The attendance sheet has side columns noting crops, rivers, and reservoirs that respond to each season's performance. A strong monsoon might fill reservoirs to capacity and yield bumper harvests. A weak monsoon might strain water supplies and reduce agricultural output. The pattern is neither good nor bad, it simply is, and societies have learned to work within its rhythms. It's important to clarify the difference between individual storms and the monsoon as a system. A single thunderstorm can happen almost any time and anywhere if conditions are right: heat, moisture, lift, and instability. The monsoon, by contrast, is a months-long shift in average winds, moisture availability, and pressure patterns. It doesn't guarantee rain every day. It simply increases the overall probability and organises the pattern. Some days within the monsoon season are dry. Some weeks might see little rainfall. But the large-scale setup remains in place, favouring convection and rain more often than not. On the attendance form, one row is today's storms, describing whether convection actually occurred on a given day. Another row is seasonal pattern in effect, noting whether the monsoon circulation is present. Both are logged, but they describe different scales. The monsoon is the framework. The daily storms are the individual events that occur within that framework. Scientists are studying how monsoons may change as the climate warms. This is a complex topic with many uncertainties, but some patterns are beginning to emerge. Warmer temperatures mean the atmosphere can hold more moisture, which might lead to heavier rainfall events during the monsoon season. At the same time, changes in land-ocean temperature contrasts, shifts in jet stream patterns, and alterations in sea surface temperatures could affect the strength and timing of monsoon circulations. Some studies suggest that monsoon onset dates might shift, arriving earlier or later than historical averages. Others suggest that the distribution of rainfall could change, with more intense bursts of rain separated by longer dry spells, rather than a steady, moderate pattern. The attendance sheet becomes a tool for noticing subtle drifts, onset dates shifting by a few days per decade, rainfall clusters changing in frequency, regional patterns evolving in ways that don't match the long-term record. Rather than declare sudden changes or jump to conclusions, the log collects year after year of carefully measured entries. Over time, trends become visible, and the cumulative data helps scientists understand what's changing and why. Monsoons are not chaotic intruders or unpredictable disasters. They are recurring shifts in the atmosphere's schedule, governed by sunlight, land-sea contrasts, and the physics of warm, moist air. Each year they arrive, stay for their allotted time, and depart, leaving behind another column of data in the long record. The process is as regular as the changing seasons, as predictable as the sun's path across the sky. There are variations, of course, some years stronger, some years weaker, some years early, some years late. But the fundamental pattern remains. The monsoon clocks in when the land heats up and pressure gradients form. It clocks out when the land cools down and the gradients weaken. In between, it delivers moisture, organises storms, and shapes the climate of entire continents. Picture a quiet office in the sky where winds and clouds sign in for seasonal shifts. The land sends up its request. We're hot now, we need moisture. The ocean responds, moisture is available, winds are reversing. The pressure gradient files its report, flow is established, convergence is active. The convection department marks its hours. Rising air reported, clouds forming, rain likely. Each day the afternoon shift arrives on schedule. Each evening the shift ends and the system winds down. Each week the totals are tallied. Each month the pattern is reviewed. And at the end of the season, the monsoon signs out, the winds reverse again, and the atmosphere returns to its off-season routine until the next cycle begins. The monsoon is not a storm, it's a season. It's not a single event, it's a pattern. It's not chaos, it's a schedule, and like any good schedule, it can be tracked, logged, and understood. The attendance sheet is simple: date, location, winds, pressure, moisture, convection, rainfall. Column after column, year after year, the data accumulates, the pattern repeats. The monsoon clocks in and clocks out as regular and reliable as the turning of the earth. Tonight we're not chasing dramatic rain footage or studying satellite loops of swirling storms. We're doing something quieter, opening an attendance sheet for the atmosphere. The monsoon isn't about non-stop downpours or apocalyptic flooding, though those things can happen. It's about a seasonal reversal of winds, a shift in where rising air and rain prefer to gather, a predictable reorganization of pressure patterns that happens year after year. Each monsoon simply clocks in and clocks out. Pressure patterns adjust, winds reorganize, and humid air starts showing up more often over land instead of lingering over the ocean. It's a routine event in the planet's calendar, documented and logged like any other recurring appointment. The attendance book starts with a simple observation. Land and ocean don't respond to sunlight in the same way. This uneven heating becomes the first line item in understanding how monsoons form. Land heats up quickly when the sun shines on it. Dark soil, rocky surfaces, bare ground, they all absorb solar radiation efficiently and warm the air directly above them. When the sun sets or the season changes, that same land cools down just as fast, radiating heat back into space. The ocean, by contrast, is a more patient participant. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature even a little. Sunlight penetrates deeper into the ocean, spreading warmth through, a thicker layer rather than concentrating it at the surface. The result is that oceans warm slowly and cool slowly, maintaining relatively stable temperatures across the seasons. In the pre-monsoon months, strong sunshine beats down on large continental areas, especially in the subtropics and tropics. Places like the Indian subcontinent, the Tibetan Plateau, the interior of West Africa, and the high deserts of North America absorb that sunlight and turn into enormous heat sources. The ground gets hot, the air above it gets hot, and pressure begins to drop. Meanwhile, the adjacent oceans remain cooler, and their pressure stays higher. In the attendance metaphor, heated land is the first box to get a check mark. The system is beginning to wake up. Air doesn't sit still when pressure differences develop. It moves from regions of higher pressure toward regions of lower pressure, always trying to smooth out imbalances. As land heats and pressure over continents drops, while pressure over adjacent oceans stays higher, a horizontal pressure gradient forms. This gradient isn't a sudden jolt or a violent push. It's a gentle, large-scale rearrangement of where air prefers to flow. The stronger the heating, the stronger the gradient. The stronger the gradient, the more insistent the push from ocean toward land. On the attendance sheet, the pressure difference column gets a quiet tick. The setup is complete, and now the flow can begin. Before the monsoon arrives, prevailing low-level winds might flow from land toward ocean, or they might run parallel to the coastline, depending on the season and the region. In South Asia, for example, the wintertime winds are dry northeasterlies that blow from the cold interior of the continent out toward the warmer Indian Ocean. In West Africa, the dry season features winds from the Sahara pushing southward. But as the pressure gradient builds with the coming of summer, those winds gradually reverse. They don't flip overnight. The transition takes weeks. But once it happens, the new pattern is unmistakable. Moist onshore flows replace the dry continental breezes. In South Asia, the winds turn from dry northeasterlies in winter to moist southwesterlies in summer. This change is like employees switching shifts on a schedule. One flow checks out, the opposite direction checks in. The attendance log notes the reversal, and the monsoon season is officially underway. The ocean is a huge reservoir of moisture, and when winds start blowing from sea to land, they carry water vapor inland. This is the raw material for clouds and rain. As the air travels over warm surfaces and encounters rising terrain, mountain ranges, plateaus, escarpments, it lifts, cools, and condenses. The moisture that was invisible as vapor becomes visible as clouds. In the attendance book, moisture is a separate column. Once the onshore flow has enough length and warmth, once it's been blowing steadily for days or weeks, the humidity box is considered present. The system now has fuel. Heated land doesn't just lower surface pressure, it also makes the air above it buoyant. Each day, especially in the afternoon when the sun is strongest, parcels of warm air rise from the surface. As they rise, they cool, and if they contain enough moisture, that moisture condenses into clouds. This daily convection is a routine process, happening over and over again throughout the monsoon season. With the monsoon moisture supply in place, these daily convection cycles become more frequent and more organised. The pattern is predictable. Sun heats land, air rises, clouds build, showers and thunderstorms form, rain falls, and then the storms decay as the sun sets and the surface cools. The logbook records this as a repeated daily attendance of afternoon convection. It's not chaotic, it's rhythmic. Within the larger monsoon pattern, there are features that help organise the storms. Monsoon troughs are elongated regions of low pressure that form over heated continents and nearby seas. These troughs act like organisational lines on the attendance sheet, gathering storms and enhancing the convergence of moist air. Rather than isolated thunderstorms popping up randomly across the landscape, the monsoon season features recurrent bands and clusters of clouds that line up along these troughs. The trough might sit in roughly the same position for days at a time, or it might shift slowly north or south as the season progresses. Either way, it provides a framework. The sheet now has an entry for organised low-pressure zone present. Storms know where to gather. Monsoon rainfall isn't just about surface winds and rising air. Upper-level winds matter too. When air rises from the surface, it has to go somewhere. If the winds aloft are favourable, the rising air can spread out and escape horizontally, a process called divergence. This upper-level divergence creates a kind of vacuum that allows more air to rise from below, strengthening and sustaining the updrafts. If the upper-level winds aren't cooperative, if they block or suppress the outflow, then rising air gets capped and convection weakens. This upper-level pattern acts like support staff, clearing space for new rising air to keep moving upward. On the log, a separate row tracks upper-level support. When it's present, convection has an easier time maintaining itself, and the monsoon rains are more robust. When it's absent, the system sputters. The South Asian monsoon is one of the most well-known examples, a classic tab in the attendance book. Pre-monsoon heating over the Indian subcontinent and the vast Tibetan plateau lowers surface pressure dramatically. The plateau, sitting at high elevation, acts like a huge elevated heat source, amplifying the thermal contrast. Moist air from the Arabian Sea and the Bay of Bengal flows inland as the low-level winds flip from northeasterlies to southwesterlies. The season progresses from south to north, with onset typically beginning along the southwestern coast of India in late May or early June, and then advancing northward over the following weeks. Withdrawal happens in reverse, starting in the northwest in September and retreating southward through October and November. In the file cabinet, this system has its own tab with expected arrival dates, typical progression maps, average rainfall totals, and year-by-year comparisons. The South Asian monsoon is so regular and so well documented that its onset and withdrawal are major events in the regional calendar, affecting billions of people. The West African monsoon involves a similar seasonal shift, but with its own regional character. Here, the Intertropical Convergence Zone, the ITCZ, a belt of low pressure and rising air that circles the planet near the equator, shifts northward over the African continent during the boreal summer. Moist southwesterly winds from the Gulf of Guinea move inland, feeding lines of thunderstorms and organised squall lines that march across the Sahel. As the ITCZ migrates north, the region of frequent rain also shifts. Farmers and communities track this movement closely because it determines where and when the rains will arrive. On the attendance sheet, this system's tab shows a moving band of present rain days that tracks north in June and July, reaches its northernmost position in August, and then retreats south through September and October. The pattern is less intense than the South Asian monsoon in some ways, but just as vital to the people who depend on it. The North American monsoon is a more modest but very real pattern affecting parts of Mexico and the southwestern United States. Summer heating over the high deserts, the Mexican plateau, and the Basin and Range region helps draw moist air from the Pacific Ocean, the Gulf of California, and even the Gulf of Mexico. The result is a seasonal increase in thunderstorms, especially in the afternoons and evenings, across Arizona, New Mexico, and northern Mexico. These storms bring welcome relief from the intense heat and provide a significant portion of the region's annual rainfall. Though less intense and less extensive than some other monsoons, the North American monsoon follows the same checklist: heated land, changed pressure patterns, onshore flow, and daily convection. It gets a smaller but very real attendance tab in the binder, with entries noting typical onset in early July and withdrawal by mid-September. Even once the large-scale monsoon pattern is established, storms often follow a regular diurnal cycle, a daily rhythm of building and decay. This is the monsoon clocking in each afternoon and clocking out at night. Morning hours are often quiet with partly cloudy skies and light winds. As the sun climbs higher and surface temperatures rise, convection begins to fire. By early to mid-afternoon, towering cumulus clouds dot the landscape and thunderstorms develop. These storms can produce heavy rain, lightning, gusty winds, and sometimes hail. As evening approaches and the sun sets, the surface cools, convection weakens, and the storms dissipate. Some storms propagate into the night as organised systems, but many simply fade away. From a logging perspective, the large-scale monsoon is a multi-month presence, but its rainfall often occurs in these predictable daily shifts. Each day's entries show similar patterns. Afternoon storms, present again. It's a recurring appointment, kept reliably day after day. The monsoon doesn't last forever. As seasons change and the angle and intensity of sunlight decrease, the whole system begins to withdraw. Land surfaces cool more quickly than the ocean, weakening the pressure differences that drove the onshore flow. The thermal gradient that powered the monsoon reverses or disappears. Low-level winds gradually lose their moisture-laden inland direction and revert toward winter patterns. Dry air begins to dominate again. The attendance sheet begins marking early departures. Fewer rainy days appear in the log. The monsoon troughs weaken and shift. More frequent dry spells interrupt the pattern. Finally, the system returns to its off-season routine. Dry winds, stable conditions, and the oceanic moisture source cut off from the land. The monsoon has clocked out, leaving behind another column of data in the long record. The file is updated, the totals are calculated, and the system waits for the next cycle to begin. Monsoon seasons can vary significantly from year to year. This interannual variability is carefully tracked and studied. Some years show stronger pressure gradients and more abundant moisture transport, leading to above-average rainfall. Other years are weaker, delayed, or cut short, resulting in below-average totals and potential drought. Large-scale climate patterns play a role in these differences. El Niño, a warming of the central and eastern tropical Pacific Ocean, tends to weaken monsoons in some regions, such as South Asia, by altering atmospheric circulation patterns and shifting the location of rising air. La Niña, the opposite phase with cooler than average Pacific waters, often enhances monsoons in those same regions. Other factors, like the temperature of the Indian Ocean, the strength of high-altitude jet streams, and even distant weather patterns over the Atlantic or the polar regions, can influence monsoon performance. In the attendance metaphor, some years the monsoon is early and diligent, arriving on time and delivering abundant rain. Some years it's late, with onset delayed by weeks. Some years it's quiet, with weak circulation and disappointing totals. Climatologists keep long records of these variations, noting the anomalies and searching for patterns that might improve forecasts. Monsoon behaviour is tracked using a wide array of tools and measurements. Rain gauges scattered across the landscape provide ground truth, recording daily and seasonal totals at thousands of locations. Wind. Measurements from surface stations and weather balloons capture the reversal of flow and the strength of the onshore currents. Satellite observations provide a broader view, monitoring cloud cover, rainfall estimates, sea surface temperatures, and atmospheric moisture content. All of this data is summarized into indices, numerical values that capture the state of the monsoon at any given time. These datasets form a long historical attendance sheet, showing onset dates, total rainfall, spatial patterns, and year-to-year variability. Scientists use these logs to study trends, understand the physical mechanisms at work, and refine seasonal forecasts. The file cabinet grows thicker over time, but the format remains familiar: dates, totals, anomalies, and quiet notes about what happened and why. For many regions, monsoon rains are essential for agriculture, reservoirs, and groundwater recharge. Too little rain can mean drought, crop failure, water shortages, and economic hardship. Too much rain can mean flooding, landslides, and damage to infrastructure. Yet in this story, we keep the focus on the pattern rather than the disasters. Monsoons are scheduled deliveries of water that communities have adapted to over centuries. Farmers time their planting to the monsoon's arrival. Water managers plan reservoir operations around expected seasonal inflows. Cities and villages have developed strategies for coping with both the abundance and the absence of rain. The attendance sheet has side columns noting crops, rivers, and reservoirs that respond to each season's performance. A strong monsoon might fill reservoirs to capacity and yield bumper harvests. A weak monsoon might strain water supplies and reduce agricultural output. The pattern is neither good nor bad, it simply is, and societies have learned to work within its rhythms. It's important to clarify the difference between individual storms and the monsoon as a system. A single thunderstorm can happen almost any time and anywhere if conditions are right: heat, moisture, lift, and instability. The monsoon, by contrast, is a months-long shift in average winds, moisture availability, and pressure patterns. It doesn't guarantee rain every day, it simply increases the overall probability and organises the pattern. Some days within the monsoon season are dry, some weeks might see little rainfall, but the large-scale setup remains in place, favouring convection and rain more often than not. On the attendance form, one row is today's storms, describing whether convection actually occurred on a given day. Another row is seasonal pattern in effect, noting whether the monsoon circulation is present. Both are logged, but they describe different scales. The monsoon is the framework. The daily storms are the individual events that occur within that framework. Scientists are studying how monsoons may change as the climate warms. This is a complex topic with many uncertainties, but some patterns are beginning to emerge. Warmer temperatures mean the atmosphere can hold more moisture, which might lead to heavier rainfall events during the monsoon season. At the same time, changes in land-ocean temperature contrasts, shifts in jet stream patterns, and alterations in sea surface temperatures could affect the strength and timing of monsoon circulations. Some studies suggest that monsoon onset dates might shift, arriving earlier or later than historical averages. Others suggest that the distribution of rainfall could change, with more intense bursts of rain separated by longer dry spells, rather than a steady, moderate pattern. The attendance sheet becomes a tool for noticing subtle drifts, onset dates shifting by a few days per decade, rainfall clusters changing in frequency, regional patterns evolving in ways that don't match the long-term record. Rather than declare sudden changes or jump to conclusions, the log collects year after year of carefully measured entries. Over time, trends become visible, and the cumulative data helps scientists understand what's changing and why. Monsoons are not chaotic intruders or unpredictable disasters. They are recurring shifts in the atmosphere's schedule, governed by sunlight, land-sea contrasts, and the physics of warm, moist air. Each year, they arrive, stay for their allotted time, and depart, leaving behind another column of data in the long record. The process is as regular as the changing seasons, as predictable as the sun's path across the sky. There are variations, of course, some years stronger, some years weaker, some years early, some years late, but the fundamental pattern remains. The monsoon clocks in when the land heats up and pressure gradients form. It clocks out when the land cools down and the gradients weaken. In between, it delivers moisture, organises storms, and shapes the climate of entire continents. Picture a quiet office in the sky where winds and clouds sign in for seasonal shifts. The land sends up its request. "We're hot now, we need moisture." The ocean responds, "Moisture is available, winds are reversing." The pressure gradient files its report. Flow is established, convergence is active. The convection department marks its hours. Rising air reported, clouds forming, rain likely. Each day the afternoon shift arrives on schedule. Each evening the shift ends and the system winds down. Each week the totals are tallied. Each month the pattern is reviewed. And at the end of the season the monsoon signs out, the winds reverse again, and the atmosphere returns to its off-season routine until the next cycle begins. The monsoon is not a storm, it's a season. It's not a single event, it's a pattern. It's not chaos, it's a schedule, and like any good schedule, it can be tracked, logged, and understood. The attendance sheet is simple: date, location, winds, pressure, moisture, convection, rainfall. Column after column, year after year, the data accumulates. The pattern repeats. The monsoon clocks in and clocks out, as regular and reliable as the turning of the earth. But within this reliable framework, there are subtleties worth noting. The monsoon doesn't arrive everywhere at once, and it doesn't affect all places equally. Think of it as a progressive wave of atmospheric reorganization that sweeps across a region over the course of weeks. In South Asia, the onset begins in Kerala, on the southwestern tip of India, and then marches northward and northwestward across the subcontinent. The Arabian Sea branch brings moisture to the western coast and the western Ghats, while the Bay of Bengal branch feeds the eastern regions and eventually pushes into the Indo-Gangetic Plain. Each area has its own expected arrival window, and meteorologists track these dates closely, comparing them to historical normals. A delay of even a week can have significant implications for agriculture, so the timing is logged meticulously. The attendance sheet for the South Asian monsoon isn't just one line, it's a series of entries for different regions, each with its own clock-in date. Similarly, the retreat of the monsoon is gradual and organised. The northwestern regions of India and Pakistan see the monsoon withdraw first, usually in early September. The winds weaken, the moisture supply dwindles, and the rains become less frequent. By mid-September, much of northern India transitions to drier conditions. Southern regions hold on to the monsoon longer, sometimes into early November. This phased withdrawal is tracked and recorded, with each region's clock-out date noted. The pattern is so consistent that farmers and planners can build their calendars around it, knowing when to expect the last significant rains and when to prepare for the dry season. The West African monsoon has its own geography of onset and retreat. The coastal regions of the Gulf of Guinea see year-round rainfall, but the monsoon's northward migration determines when the Sahel receives its rains. In a typical year, the monsoon rain belt reaches southern Mali, Burkina Faso, and Niger in June, progresses northward into July, and then begins to retreat in August and September. The exact position of this rain belt on any given week can mean the difference between a good growing season and crop failure. Villages separated by just a few hundred kilometres might experience very different rainfall totals depending on how far north the monsoon pushes. The attendance log for West Africa is spatial as well as temporal, tracking not just when the monsoon arrives but where the rain actually falls. In North America, the monsoon's geography is defined by mountain ranges and deserts. The Sierra Madre Occidental, the Mogollon Rim, and the ranges of southern Arizona channel moisture and create preferred zones for thunderstorm development. The cities of Tucson and Phoenix see a marked increase in rainfall during July and August, with afternoon and evening thunderstorms becoming a regular feature. These storms are often localized, dropping heavy rain on one neighborhood while leaving another a few miles away completely dry. The attendance sheet for the North American monsoon includes spatial variability at a fine scale, with rainfall totals varying dramatically over short distances. A weather station in the mountains might record several inches of rain on a given day, while a station in the valley below sees nothing. The mechanisms that drive these regional patterns are variations on the same basic theme. Differential heating between land and ocean creates pressure gradients. Those gradients drive winds. The winds transport moisture. Moisture plus heat plus lift equals clouds and rain. But the details matter. The shape of coastlines, the height and orientation of mountain ranges, the temperature of nearby ocean currents, the presence or absence of large lakes. All of these factors modify the basic pattern and create regional character. The South Asian monsoon is so intense partly because of the Himalayas and the Tibetan Plateau, which act as enormous elevated heat sources and also block cold air from the north. The West African monsoon is shaped by the Sahara Desert, the Gulf of Guinea, and the complex topography of the African continent. The North American monsoon is influenced by the Gulf of California, the Mexican Plateau, and the orientation of mountain ranges that guide moisture flow. There are also intra-seasonal variations within a single monsoon season. The monsoon doesn't deliver rain at a steady rate from onset to withdrawal. Instead, it pulses. There are active periods when the monsoon trough deepens, moisture surges inland, and rainfall is widespread and frequent. These active periods might last a week or two, bringing daily thunderstorms and soaking rains. Then there are break periods, when the trough weakens or shifts, moisture flow decreases, and rainfall becomes sparse. During a break, skies might clear for several days in a row, temperatures rise, and the landscape dries out. Then the active phase returns and the cycle repeats. These active and break periods are a natural part of the monsoon's internal rhythm. On the attendance sheet, they appear as fluctuations within the overall seasonal pattern. Active phase, July 8th or 18. Break phase, July 19th to 25. Active phase resumed, July 26th. The monsoon is present for the entire season, but its intensity waxes and wanes. These intra-seasonal oscillations can be influenced by larger atmospheric waves that propagate around the tropics. The Madden-Julian Oscillation, or MJO, is one such wave, characterized by enhanced convection that moves slowly eastward across the Indian and Pacific Oceans. When the MJO's active phase coincides with a monsoon region, it can enhance rainfall and trigger an active period. When the MJO's suppressed phase arrives, it can initiate a break. Forecasters monitor the MJO and other tropical waves to anticipate these shifts and provide advance warning of heavy rain or dry spells within the monsoon season. The attendance log gains another layer of detail, not just whether the monsoon is present, but what phase of its internal cycle it's in. The relationship between monsoons and topography deserves closer attention. Mountains don't just sit passively in the landscape, they actively shape the monsoon. When moist air encounters a mountain range, it's forced to rise. As it rises, it cools and moisture condenses, producing clouds and precipitation on the windward side of the range. This is called orographic lift, and it's a powerful rainfall enhancer. The Western Ghats in India, the Khasi Hills in northeastern India, the highlands of Ethiopia in East Africa, the Sierra Madre in Mexico, all of these ranges experience intense monsoon rainfall because of orographic lift. Some of the wettest places on Earth are located on the windward slopes of mountains in monsoon regions. Mawsynram and Cherrapunji in India, for example, receive staggering amounts of rain during the monsoon season, with annual totals often exceeding 10 metres. The leeward side of the range, by contrast, sits in a rain shadow, receiving much less moisture. The air has already lost much of its moisture on the windward ascent, so the descending air on the leeward side is drier and warming. The attendance sheet has separate entries for windward and leeward zones, reflecting these dramatic differences. Monsoons also interact with large bodies of water beyond the oceans. In South Asia, the Bay of Bengal acts as a moisture reservoir and a region of active storm development. Low-pressure systems and depressions frequently form over the bay during the monsoon season, drawing in moisture and then tracking westward or northwestward across India, bringing widespread rain. These systems are carefully monitored and tracked, and their presence is noted in the log. A strong depression can deliver several days of continuous rain across a wide area, significantly boosting seasonal totals. The Arabian Sea plays a similar role for the western branch of the monsoon, feeding moisture to the west coast of India and occasionally spawning cyclonic systems that enhance rainfall. In Africa, Lake Victoria and other large lakes can modify local monsoon patterns. The lakes act as local moisture sources and can enhance convection in their vicinity. In North America, the Gulf of California provides moisture for the North American monsoon, and the Sea of Cortez helps sustain the flow of humid air into the southwestern deserts. These bodies of water are logged as contributing factors in the moisture budget, small but important entries in the overall accounting. The role of soil moisture in the monsoon is another subtle but important factor. When the monsoon arrives and rain begins to fall, the land surface is initially dry, especially after months of dry season. The first rains are absorbed quickly, recharging soil moisture and groundwater. As the season progresses and the soil becomes saturated, more of the rainfall runs off into streams and rivers rather than soaking in. But the presence of moist soil also feeds back into the atmosphere. Evaporation from wet soil adds moisture to the air near the surface, making it easier for convection to develop. This feedback can enhance subsequent rainfall events. Conversely, if a break period allows the soil to dry out significantly, it can make it harder for convection to restart when the active phase returns. The attendance log tracks not just rainfall, but also soil moisture levels, river flows and reservoir storage, recognizing that the land surface is an active participant in the monsoon system, not just a passive recipient of rain. Vegetation also plays a role. Forests and croplands transpire water into the atmosphere, adding moisture to the boundary layer. During the monsoon season, when vegetation is green and growing, transpiration rates are high, contributing to the local moisture budget. Some studies suggest that deforestation and changes in land use can weaken local monsoon circulations by reducing this moisture recycling. The attendance sheet might include notes on land cover, forest cover stable, transpiration contributing as expected, or, in regions experiencing rapid land use change, deforestation observed, possible reduction in moisture recycling. These are small adjustments, but over time they can influence the character of the monsoon in a given area. Urban areas introduce their own modifications to monsoon patterns. Cities are heat islands, with temperatures often several degrees warmer than surrounding rural areas due to heat-absorbing pavement, buildings, and reduced vegetation. This urban heating can enhance convection, sometimes triggering or intensifying thunderstorms downwind of the city. The urban heat island effect gets logged as a local factor influencing storm frequency and intensity. On the other hand, urbanization can reduce infiltration and increase runoff, leading to rapid flooding during heavy rain events. The monsoon delivers the same amount of rain, but the urban landscape responds differently than natural terrain. The attendance sheet includes entries for urban versus rural responses, noting how the same atmospheric pattern produces different outcomes depending on the surface below. The monsoon's influence extends to ocean processes as well. During the monsoon season, strong winds over the ocean can drive coastal upwelling, bringing cold, nutrient-rich water to the surface. This upwelling supports marine productivity and fisheries. In the Arabian Sea, monsoon winds drive upwelling along the coast of Oman and Somalia, creating one of the most productive marine ecosystems in the world. The timing and strength of the monsoon directly affect the timing and intensity of this upwelling. Fishermen track the monsoon not just for the rain it brings on land, but for the changes it brings to the ocean. The attendance log expands to include ocean conditions, sea surface temperatures, upwelling indices, and fishery productivity, all linked to the monsoon cycle. The historical record of monsoons stretches back centuries, far beyond the era of modern instruments. Paleoclimate researchers study monsoon variations using proxy data. Tree rings, lake sediments, cave formations, ice cores, and ancient written records. These proxies reveal that monsoons have varied over long timescales, responding to changes in Earth's orbit, ice sheet extent, and greenhouse gas concentrations. During the mid-Holocene, several thousand years ago, monsoons were generally stronger in many regions due to changes in Earth's orbital parameters that enhanced summer heating in the Northern Hemisphere. Written records from China, India, and Egypt document monsoon failures and floods over the past few millennia, providing a cultural memory of variability. The attendance sheet, in its long-term form, is not just a product of the modern era. It's a continuation of record-keeping that humans have engaged in for as long as they've depended on seasonal rains. The format has changed, from inscriptions on stone to handwritten ledgers to digital databases, but the fundamental purpose remains: to track the arrival, performance, and departure of the rains. Modern forecasting of monsoon behaviour is a major scientific and operational challenge. Seasonal forecasts attempt to predict whether a monsoon season will be above normal, near normal, or below normal in terms of total rainfall. These forecasts are issued weeks or months in advance, based on statistical models, dynamical climate models, and an understanding of factors like El Niño and sea surface temperature patterns. The accuracy of these forecasts has improved over the decades, but uncertainties remain. Monsoon systems are complex, with many interacting components, and small changes in initial conditions can lead to different outcomes. Forecasters present their predictions probabilistically. 60% chance of above normal rainfall, for example, acknowledging the inherent uncertainty. The attendance sheet in this context becomes a tool for verification. After the season ends, the forecast is compared to what actually happened, and the results are logged. Over time, this feedback loop helps improve the models and methods. Within a monsoon season, shorter-range forecasts predict day-to-day and week-to-week variations. When active and break phases will occur, where heavy rainfall is expected, when and where flooding might be a concern. These forecasts rely on weather models, satellite data, and real-time observations. They're updated daily, providing guidance for farmers, water managers, disaster response teams, and the general public. The attendance log feeds into these forecasts and is updated by them, creating a continuous cycle of observation, prediction, verification, and adjustment. The monsoon also interacts with human-induced climate change in ways that are still being understood. While the basic physics of land-sea heating contrasts won't disappear, the magnitude and character of monsoons may shift. Some modelling studies suggest that global warming could intensify monsoon rainfall in some regions because a warmer atmosphere holds more moisture. Other studies suggest that changes in aerosol pollution, tiny particles in the atmosphere from industrial activity and biomass burning, could affect monsoon strength by altering the amount of sunlight reaching the surface and changing cloud properties. Aerosols can either enhance or suppress rainfall depending on their type and concentration, adding another layer of complexity. The attendance log in the 21st century is not just a record of natural variability, it's also a record of how human activities are reshaping the atmosphere and, potentially, the monsoon itself. Adaptation to monsoon variability is an ancient practice, but it continues to evolve. Traditional water harvesting systems like tanks and stepwells in India were designed to capture and store monsoon rain for use during the dry season. Modern infrastructure, dams, reservoirs, irrigation networks, serves a similar purpose on a larger scale. Agricultural practices have been adapted to the monsoon calendar, sowing dates timed to coincide with expected onset, crop varieties selected for their ability to thrive with monsoon rainfall, and diversification strategies to manage risk. Urban planning is increasingly considering monsoon impacts, with efforts to improve drainage, reduce flood risk, and manage stormwater sustainably. The attendance sheet informs all of these efforts, providing the data needed to design infrastructure, plan planting schedules, and manage water resources. The monsoon's cultural significance is profound. In many regions, the arrival of the monsoon is celebrated with festivals, songs, and rituals. It's a time of renewal, relief from the heat, and hope for a good harvest. Literature, music, and art have long been inspired by the monsoon. Ancient Sanskrit poetry describes the onset of the rains with vivid imagery. Indian classical music has specific ragas associated with the monsoon season. Monsoon festivals in South Asia mark the end of the dry, hot pre-monsoon period and the beginning of cooler, greener conditions. The monsoon is not just a meteorological phenomenon, it's woven into the fabric of culture and identity. The attendance sheet in this light is not merely a scientific record, but a chronicle of a deeply human relationship with the rhythms of the atmosphere. There are also ecological dimensions to the monsoon. Many ecosystems are adapted to the seasonal pulse of moisture. Deciduous forests shed their leaves during the dry season and burst into new growth when the monsoon arrives. Grasslands green up and support grazing animals. Wetlands fill and become habitats for migratory birds. The timing of plant flowering, insect emergence, and animal breeding is often synchronized with the monsoon. Disruptions to the monsoon, late onset, early withdrawal, weak rains, can ripple through these ecological systems, affecting food webs and biodiversity. The attendance log, in ecological applications, is used to study phenology, the timing of natural events and how they correlate with climate patterns. The monsoon also shapes river systems and sediment transport. During the monsoon season, rivers swell with runoff from heavy rains. Sediment eroded from hillsides and agricultural fields is carried downstream, sometimes building deltas and floodplains, sometimes causing problems with reservoir sedimentation. The annual flood pulse in rivers like the Ganges, the Brahmaputra, the Mekong, and the Niger is driven by the monsoon. These floods are natural events that have historically supported agriculture by depositing nutrient-rich sediments on floodplains. Modern river management often tries to control or dampen these floods, but the monsoon's influence remains fundamental. Hydrologists track river discharge alongside monsoon rainfall, logging flow rates, sediment loads, and flood extents as part of the larger monsoon record. Monsoons can also trigger natural hazards. Intense rainfall can cause flash floods, landslides, and debris flows, especially in mountainous terrain. The same orographic lift that produces record rainfall totals can also create dangerous conditions on steep slopes. Soil becomes saturated, slopes become unstable, and gravity takes over. In densely populated regions, these hazards can lead to loss of life and property. Disaster management systems monitor monsoon conditions closely, issuing warnings and coordinating response efforts. The attendance log becomes a tool for hazard assessment, identifying high-risk periods, tracking rainfall intensity, and comparing current conditions to historical thresholds. At the same time, the monsoon is a source of life and prosperity. It fills aquifers, replenishes lakes, and supports ecosystems. It enables agriculture in regions that would otherwise be too dry to farm. It cools the air and provides relief from extreme heat. The dual nature of the monsoon, both hazard and blessing, is reflected in the way societies engage with it. The attendance sheet records both the benefits and the risks, logging rainfall totals alongside flood damages, crop yields alongside landslides. The goal is not to eliminate the monsoon or control it, but to understand it well enough to maximise benefits and minimise harm. The scientific understanding of monsoons continues to deepen. New satellite instruments provide ever more detailed views of atmospheric moisture, cloud properties, and rainfall rates. Advances in computing power allow for higher resolution climate models that can simulate monsoons with greater fidelity. Field campaigns deploy instruments across monsoon regions to collect data on winds, temperature, humidity, and aerosols, filling in gaps in the observational record. International collaborations bring together researchers from multiple countries to study monsoons as global phenomena with regional expressions. Each new dataset, each new model run, each new analysis adds another entry to the attendance log, refining our understanding of how monsoons work and how they might change. The monsoon is a testament to the interconnectedness of Earth's systems. It links the ocean to the land, the tropics to the subtropics, the surface to the upper atmosphere. It connects weather to climate, short-term variability to long-term patterns. It ties together physical processes, ecological systems, and human societies. The attendance sheet, in its simplest form, is a list of dates and numbers. But behind those numbers is a story of energy, moisture, motion, and change. A story that repeats every year but is never exactly the same twice. As the night deepens and the rhythm of your breathing slows, you can imagine that quiet office in the sky still at work. The logs are being updated even now. Somewhere a monsoon is in full swing, clouds towering, rain falling, rivers rising. Somewhere else, a monsoon is withdrawing, winds shifting, skies clearing, the dry season returning. The attendance sheet is always open, always recording. The monsoon clocks in, does its work and clocks out, as faithful as the Earth's rotation, as predictable as the seasons, as essential as the sun. The pattern continues, reliable and patient, waiting for the next cycle to begin. The next story is about to begin. Please relax and enjoy.